Welcome to Sleepy Stories, where knowledge unfolds slowly and gently, allowing your mind to learn even as your body drifts toward rest. Here, curiosity and calm share the same quiet space. You are invited to listen, not with urgency, but with ease, to let understanding arrive in its own rhythm. If sleep does not come right away, there is no need to chase it. The mind, like the earth itself, moves in cycles, sometimes erupting with energy, sometimes settling into stillness. Let your thoughts cool, let your breath align with the steady pulse of the planet. And if these calm nights help you find rest and wonder, we gently ask you to like and subscribe so that more journeys like this may continue to flow. Tonight, we travel inward to the hidden fires that shape our world. The story of volcanoes is the story of Earth's own breath, a force both creative and destructive, patient and sudden. Every mountain, island, and plain has, at some point in deep time, been touched by molten rock. To understand volcanoes is to look into the planet's interior, to trace the heat that still burns from its birth more than 4 billion years ago. This heat did not vanish when the surface cooled. It gathered, trapped beneath layers of stone, rising through fractures in slow motion. What we see as eruption is not anger, but release, the planet balancing itself, shedding energy, renewing its surface. Beneath your feet, more than 20 miles down, lies the mantle, a realm of slow movement where rock flows like thick honey under immense pressure. Here, temperatures reach thousands of degrees, and minerals melt into magma. It is not a uniform ocean of fire, but a dynamic mixture of solid and molten regions, constantly shifting. This is Earth's inner ocean, invisible yet powerful, circulating like blood through the body of the planet. Convection currents within it carry heat upward, pushing and pulling the crust above. Where these forces meet, at fractures or subduction zones, volcanoes are born. Scientists have learned to read the planet's inner motion through seismic waves, satellite data, and the chemistry of erupted rocks. Each eruption reveals something about the deep engine driving our world. Some volcanoes rise quietly from the sea, spreading sheets of basalt that build new land. Others explode with sudden violence, sending ash high into the stratosphere, altering climate for months or years. These extremes are not opposites but expressions of the same principle, energy moving from high pressure to balance. For as long as humans have watched the horizon, volcanoes have inspired awe and fear. Ancient observers saw them as the breath of gods, gateways to the underworld or symbols of creation. Modern science replaced myth with measurement, but the sense of reverence remains. To stand before an active volcano is to witness time itself in motion, to see the deep earth made visible for a brief moment before cooling again into stillness. Tonight, as you listen, imagine the slow rhythm of our planet beneath its quiet surface. The continents drift like rafts over the mantle, colliding and parting in endless cycles. Beneath them, magma gathers in pockets of glowing red, waiting for a chance to rise. In that image lies the truth of our world. Constant change hidden beneath apparent calm. The same dynamic that once built mountains now sustains life through fertile soil and atmosphere. Without volcanoes, the world as we know it would never have formed. So as you rest, picture the planet not as something solid and still, but alive with motion. The surface may seem quiet tonight, yet deep below, heat continues to move, reshaping the crust, recycling the elements, creating and destroying worlds over geological ages. Let that thought settle like cooling lava, steady, slow, inevitable. The earth breathes through fire, and in that breath lies the story of every mountain, every island, and perhaps your own rhythm of rest. Deep below the crust lies the engine that feeds every volcano. Here, pressure and temperature work together to melt ancient rock, turning it into a fluid called magma. The story starts with heat left over from the formation of the planet and with the steady warmth released by the decay of radioactive elements in the mantle. Over very long spans of time, this heat does not vanish. It rises, softens solid rock, and gathers into pockets that behave like slow, buoyant reservoirs beneath the surface. Because magma is less dense than the rock around it, it begins to move upward. The ascent is not dramatic. It is measured in centimeters per year, a rate so gentle that it would look like stillness to a human observer. As it rises, the melt releases dissolved gases and alters the crystal structure of the rocks it touches. This quiet movement can be detected by careful listening. Scientists watch the journey with seismic waves, the vibrations that travel through the planet after earthquakes. Where the waves speed up, rock is cooler or more rigid. Where the waves slow down, rock is hotter or partially molten. By combining many paths through the earth, researchers build images of the hidden interior. A magma body becomes visible not to the eyes but to the mathematics of travel time and the patient comparison of many small signals. The mantle itself is not a single uniform sea. Some regions melt easily because they contain minerals that relax at lower temperatures or because traces of water lower the melting point. Other regions resist melting because their minerals are tightly bonded or because pressure is high. The crust above also matters. Where it is thin or fractured, magma has an easier path. Where one plate sinks beneath another in a subduction zone, water and sediments ride down into the mantle and trigger melting. That melt then rises and feeds chains of volcanoes that form arcs along the edges of oceans. To picture this process, imagine a slow exhale from a warm interior into a cooler world. Heat generated near the core moves toward the surface and finally escapes into space. Every eruption, whether a mild flow or a violent blast, is a step in that cooling journey. Without such steps, pressure would accumulate and the planet would hold too much energy inside. Eruptions are not failures of stability. They are the mechanism by which the Earth maintains balance. Magma changes as it travels. Some of it stalls in chambers and cools slightly, becoming thicker and more viscous. Some of it mixes with other melts. Some of it absorbs fragments of the rock it passes through and takes on new chemistry. These changes matter because they decide how the magma will behave when it reaches the surface. A fluid basalt will spread in broad sheets and build gentle slopes. A sticky, silica-rich melt will trap gases until they expand with enough force to shatter rock and send ash high into the sky. Volcanoes therefore remind us that the planet we stand on is not fixed. Beneath the thin crust, energy circulates in large loops that reach from the deep mantle nearly to the air. The next time you picture a mountain against a quiet sky, hold two truths at once. The mountain is still to your senses. The mountain is the latest shape of a very slow motion, a form taken on by heat that began its journey long before any observer arrived. Let that thought settle. Beneath the calm of night, the same ancient forces continue to move, not with urgency, but with patience. They are not racing toward an end. They are maintaining a steady conversation between hot and cold, between depth and surface. Every eruption you have ever seen in an image or a film began as a gentle, buoyant drift in the dark. Every island that rises from the sea owes its outline to quiet physics carried out over unimaginable spans of time. In that perspective, fear relaxes and curiosity can take its place. The ground is alive, and its life has a rhythm that favors balance. The surface of the earth looks permanent, yet it is built from plates that move. These plates are broad fragments of the outer shell, floating on a mantle that behaves like a very slow fluid. Their motion is powered by the transfer of heat from the interior towards space. As warm material rises and cool material sinks, the plates respond to the slow drag and push of that circulation. Mountains, earthquakes, and volcanoes are the visible results of this hidden transport of energy. When plates diverge, they move apart and leave space for magma to rise and create new crust. The most dramatic examples are mid-ocean ridges, long chains of underwater mountains that circle the planet. There, molten rock wells up to fill the gap, freezes into basalt, and adds a fresh stripe to the ocean floor. Over time, the new crust is carried away from the ridge, like cargo on a conveyor. The Atlantic basin, for example, grows wider as melt repeatedly rises and hardens along the ridge that runs between the continents. Most of these eruptions are not seen by human eyes, yet they account for a large portion of the planet's volcanic output. Renewal happens in darkness and cold water, not only in bright fountains of lava on land. Where plates converge, the story changes. If an oceanic plate meets a continental plate, the denser oceanic plate bends and slides beneath its partner. This process is called subduction. As the slab descends, it takes water and sediments with it. The water lowers the melting point of surrounding rock and generates magma that rises to feed chains of volcanoes on the surface above. These arcs outline the boundaries around the Pacific Ocean and explain why so many explosive volcanoes cluster there. The magma in such zones often holds more dissolved gases. When that gas expands near the surface, it can drive a sudden, violent release of ash and rock. Sometimes two continents collide and neither can sink. The crust thickens and folds into high ranges. Volcanoes are usually scarce in these regions, yet heat and pressure still rise within the deep roots of the mountains. Even without fire on the peaks, there is warmth within the base. Scientists track the motion of plates with networks of satellites that can detect a shift of a few millimeters per year. These tiny rates would not matter in a single lifetime, but over millions of years they reshape the globe. Continents drift apart, wander, and meet again. Ocean basins open and then close. The outline of the world you know is one frame in a long animation and not the final map. To understand how this motion relates to volcanoes, imagine the plates as lids that both confine and channel the planet's heat. At spreading centers, the lids open slightly, and melt reaches the surface in steady, manageable flows. At subduction zones, the lids are pressed together, and melts are generated with more gas and more complexity, which sets the stage for sudden, powerful eruptions. The difference is not magic. It is chemistry, temperature, pressure, and the geometry of the boundaries. Hold this image as you rest. The continents move like slow rafts on a deep current. Volcanoes are the points where that current touches air. The ground under your home, which feels still and safe, is part of this wider migration. Stability is not the absence of motion, it is the regularity of motion through time. When you picture the planet breathing, picture this as the breath, plates parting, plates meeting, and heat moving steadily upward to find release. Along the seams where plates meet, volcanoes organize themselves into patterns that reveal the inner architecture of the planet. These margins are the places where the crust is stretched thin, crumpled thick, or pulled downward into the mantle. They are also the places where magma finds weaknesses that act like doors. When enough pressure builds, the doors open and the earth vents heat. Around the Pacific Ocean there is a vast chain of such doors. Many of the world's active volcanoes stand along this boundary. In these regions, an oceanic plate slides beneath either a continental plate or another oceanic plate. As the slab descends, it carries water and sediments into the mantle. Water loosens the bonds in minerals and lowers the melting point of the rock. The resulting magma tends to be richer in silica and in dissolved gases. As it rises, the pressure drops and the gas expands. If the melt is thick, the gas cannot escape easily. When it finally breaks free, the result can be an explosive eruption that sends ash high into the atmosphere and covers wide areas with tephra and pumice. At divergent boundaries, by contrast, the crust pulls apart and magma ascends without much resistance. The lava there is typically basaltic and fluid. It pours from fissures, spreads out in sheets, and cools into dark rock that builds the ocean floor or broad plateaus on land. The shapes created by these two styles differ. A stratovolcano grows tall and steep from alternating layers of ash and lava. A shield volcano grows wide and gentle from repeated flows of fluid basalt. The minerals in cooled lava record both chemistry and history. Tiny magnetic grains align with the planet's magnetic field as the rock solidifies. Over long periods, the field reverses direction, and those grains keep the record. By reading the stripes of magnetic orientation on the sea floor, scientists confirm that new crust forms at ridges and that the plates move. Gas bubbles trapped in rock can reveal the depth at which the melt formed and the pressure it experienced. Even the size of crystals can speak to the speed of cooling. The stone itself becomes a logbook. Living near these margins has always meant living with trade-offs. Ash can damage lungs and roofs, yet the same ash can weather into soil that feeds crops for generations. Lava can bury a road, yet a new coastline can attract life and people to fresh ground. Many communities accept this rhythm. They adapt with monitoring networks, evacuation plans, and building codes designed to reduce risk. Science does not remove danger, but it can turn surprise into preparation and fear into informed action. As you visualize these boundaries tonight, see the planet as strong because it moves, not fragile because it shifts. Pressure rises and then releases. Energy gathers and then finds a path outward. This is not chaos. It is a cycle that has kept the planet geologically alive. The crust may tremble, a cone may grow, ash may fall like grey snow. Yet after each episode, heat is reduced and the system returns to balance. In that balance there is a kind of calm that mirrors the breath you are taking now. Far below the crust the mantle moves, not quickly, but persistently. It is solid rock that flows when given enough time, shaped by heat and pressure into a slow circulation called convection. This motion is the deep heartbeat of geology. It carries heat upward from the interior and carries cooler material downward to be warmed again. Out of that flow come the forces that shift plates, build ridges, and feed volcanoes. Convection begins where temperatures are greatest, near the core. Warm, slightly less dense mantle rock rises toward the surface. As it rises, it cools and becomes denser, and that cooler material sinks. The result is a set of loops that trade heat between depth and crust. The speed is modest by any daily measure, but persistence is power. Over spans of time that stretch beyond human history, those loops sculpt continents and basins. Scientists cannot watch this directly, so they infer its shape with tools. Seismic tomography compares the travel times of waves from many earthquakes to map regions that are hotter or cooler. Hotter areas slow the waves, cooler areas speed them up. Gravity measurements add another layer, and the chemistry of volcanic rocks adds a third. When a plume of hot material rises, the rocks it produces can carry a signature that points back to mantle sources. Hot spots at the surface, such as the long chain of islands in the Central Pacific, align with these deep sources and show that not all volcanic activity happens at plate boundaries. The mantle also holds a memory of the earliest chapters of the planet. Fragments of very old crust may be carried down at subduction zones and stored for a long time before they are melted and returned to the surface. Minerals can trap traces of that journey. By studying them, researchers connect modern eruptions to ancient events. The circulation is not a simple conveyor that turns once and stops. It is a living system that recycles material, alters it, and returns it in new form. This circulation keeps the planet active, Bodies that cooled faster or lacked sufficient internal heat lost this kind of motion and became geologically quiet. Without convection, there would be little plate motion, and without plate motion, volcanoes would be fewer and the surface would evolve slowly. Heat would remain trapped for longer, and the exchange of gases between interior and atmosphere would diminish. Life as we know it benefits from this ongoing trade between depths and air. To understand volcanoes in this frame is to view them as valves in a pressure system. They are the points where heat and material leave the interior in bursts or in steady flows. The style of that release depends on the path the melt took, the chemistry it acquired, and the conditions it met near the surface. A calm shield volcano marks a long, steady supply of basalt. A tall, layered cone marks stages of storage, gas buildup, and release. As you rest, picture this motion without hurry. Picture loops of warm rock rising and cool rock sinking, like a very slow tide that never misses a beat. Every tremor you have heard about began as a whisper in this deep circulation. Every plain of black basalt, every cliff of pale ash, and every island that steps across the sea is a trace of the same patient engine. The ground beneath you is not a static platform. It is the top of a grand system designed to exchange heat with the sky and to keep the world renewing itself. Beneath the continents, the mantle keeps moving with a rhythm that does not stop. Every few centimeters of motion per year, every slow drift of molten rock adds up to a steady transfer of energy that keeps the planet alive. The surface may sleep, but the interior never does. It breathes through cycles of pressure and release, a pattern so constant that it becomes easy to forget it is happening at all. Volcanoes are the visible moments in that rhythm, brief exhalations that let the heat escape. Between them, the world appears calm, yet balance continues quietly underfoot. Inside a magma chamber, molten rock behaves like a living fluid. The upper layers cool and crystallize while deeper regions remain hot and buoyant. Gas bubbles form and collapse, mixing the melt in slow convection loops. Over time, pressure builds. The surrounding rock flexes, cracks, and records that pressure as small earthquakes. Sensitive instruments can detect these tremors long before an eruption. Satellite radar measures the swelling of the ground by just a few centimeters, enough to warn scientists that magma is moving upward. Even gases rising through cracks tell a story. When sulfur dioxide or carbon dioxide concentrations change, researchers know the chamber below is evolving. Every detail, from tremor to vapor, is part of the conversation between Earth's deep interior and its surface air. For humans, that conversation is mostly inaudible. Our lives pass too quickly to notice the pauses between eruptions or the way new crust cools and hardens. Yet understanding this rhythm gives perspective. The planet does not hurry. It regulates itself with patience measured in millions of years. Eruptions that seem catastrophic from a human view are minor adjustments within that larger scale. They release pressure so the deeper mantle can keep flowing in equilibrium. Some volcanic systems remain active for hundreds of thousands of years, cycling through quiet dormancy and renewed activity. Others die after a single eruption when their magma source is exhausted. In both cases, the same principle governs the outcome. Heat must travel upward, and the planet will find a path for it. The crust may thicken, fracture, or rise, but energy always completes the journey. Without that movement, Earth would become stagnant, its surface locked and lifeless. This awareness can shape how we rest tonight. The same patience that guides the mantle can guide the mind. Breathing slowly, you mimic the planet's own pace. Inhale as pressure builds. Exhale as it releases. Each breath mirrors the silent exchange between interior and exterior, between warmth and coolness. There is no urgency in this rhythm, only steadiness. You do not need to force sleep. It will come naturally when balance returns, the way an eruption is followed by calm. For a moment, picture a cross-section of the planet beneath you. Layers of rock glow faintly with residual heat. Streams of magma rise through narrow conduits, pause, and descend again as they cool. The surface above them is quiet. Forests, oceans, cities resting on a shell, only a few dozen kilometers thick. That shell bends slightly, flexes gently, and settles again. The world is not fragile. It is elastic. It carries us through time with a strength born from motion. When you feel the pulse of your own heartbeat, know that it is not separate from this geologic rhythm. Both follow the same physics of balance. Pressure rises and must be eased. Energy accumulates and must be released. The difference is scale, not principle. Just as your body uses breath to cool and renew itself, the earth uses volcanoes to regulate its inner fire. Awareness of that shared logic can be comforting. It reminds us that rest and renewal are natural outcomes of release, not interruptions of activity. Tonight, as you close your eyes, imagine the ground beneath you exhaling a slow current of warmth into the dark. Nothing dramatic, only a steady diffusion of energy. It moves upward, dissipates into the air, and leaves the deep layers slightly cooler. The surface remains peaceful. The stars shine above a planet that continues its quiet work below. In that realization, tension can melt. The world maintains itself without hurry. You can allow yourself the same permission. Every volcano begins far below the surface, as molten rock gathers in a chamber where pressure quietly builds. The chamber forms when buoyant magma from the mantle reaches a layer of rock too strong to let it pass. There it spreads sideways, carving a pocket of fluid heat inside the crust. Some chambers span only a few kilometers, others extend for dozens. The melt inside is a mixture of crystals, liquid, and dissolved gases such as water vapor, carbon dioxide, and sulfur dioxide. These gases are the restless part of the system. They expand when pressure drops, and their behavior decides whether a volcano will whisper or roar. As magma accumulates, its temperature and chemistry evolve. Crystals form along the walls and sink or rise depending on their density, while the remaining liquid becomes richer in silica. Silica increases viscosity, making the magma thicker and more resistant to flow. In this slow transformation, the foundation for every eruption is set. A fluid basaltic melt can travel through cracks and reach the surface in steady flows. A sticky rhyolitic melt can trap gas until the pressure surpasses the strength of stone. Geophysicists monitor these invisible processes with instruments that measure ground movement, seismic vibration, and the chemistry of volcanic gases. A few millimeters of uplift, a cluster of tiny earthquakes, or a sudden spike in sulfur emissions can mean that magma is rising. Satellites orbiting hundreds of kilometers above Earth detect subtle changes in gravity and magnetism that betray magma migration. Each signal is a clue, and together they form an early warning system that saves lives. When pressure finally exceeds the weight of the overlying rock, fractures open. The magma forces its way upward, often along existing faults created by earlier events. As it ascends, the confining pressure decreases, allowing gases to come out of solution and form bubbles. These bubbles expand rapidly, pushing the melt faster. The upward flow accelerates until the magma reaches the surface and breaks through. What happens next depends on how much gas remains trapped. If it escapes smoothly, lava will pour quietly from vents, creating rivers of molten rock. If the gas expands violently, the eruption becomes explosive, propelling ash and pumice high into the air. The surface manifestation of this process can take many shapes. A simple crack may produce a curtain of lava several kilometers long. A single vent may build a cone as fragments accumulate around the opening. Sometimes the summit collapses after the eruption, forming a caldera that later fills with water or new lava. Each structure tells geologists what happened below: pressure, composition, and sequence of events written in layers of stone. The chemistry of magma is influenced not only by its source but also by the rocks it passes through. When basaltic melt rises beneath continental crust rich in silica, it can melt part of that crust and absorb its components. This contamination creates hybrid magmas with unpredictable behavior. Some eruptions begin quietly and then escalate as gas content changes midway. Understanding this interaction helps volcanologists model scenarios and plan evacuations. Volcano formation also involves feedback. Once a vent opens and releases gas, the pressure in the chamber drops, often causing the eruption to wane. Cooling lava can plug the conduit, sealing the system again and allowing pressure to rebuild for the next episode. In this way, a volcano becomes cyclical, alternating between construction and rest. Each phase modifies the landscape: new rock, new cracks, new potential pathways for the future. From a distance, the creation of a volcano seems sudden, yet the groundwork spans thousands of years. Magma may linger beneath an area for centuries before breaking through. During that time, it shapes the crust quietly, altering minerals, raising ground temperature, and creating hydrothermal systems that vent steam through hot springs and fumaroles. These features are surface hints of the deeper story still unfolding. As you think about this process, imagine the planet beneath you performing these steps in silence. There is no malice in the pressure that builds, no intent in the fracture that opens. It is simply physics at work: buoyancy, gas expansion, gravity, and heat-seeking balance. What emerges at the surface is not an outburst of anger but a necessary exchange. The interior releases what it can no longer contain, and the crust reshapes itself to accommodate that release. In the calm that follows, new ground cools and hardens, becoming part of the landscape upon which forests, rivers, and eventually people will live. The next time you see footage of a glowing vent or a fountain of lava, remember the patience behind it. What appears violent is the end of a long conversation between deep rock and open air. Beneath the noise there is order, and within that order the world maintains its steady pulse. No two eruptions are the same, because no two magmas are the same. Each carries its own mixture of minerals, gases, and temperature, and this chemistry determines everything from color and viscosity to the shape of the volcano itself. The science of these differences explains why one mountain oozes gentle lava streams while another explodes with thunderous clouds of ash. At the heart of that contrast lies a single element: silicon, the building block of the Earth's crust. Silicon and oxygen bond to form silica, a molecule that links together into chains and networks inside molten rock. The more silica present, the thicker the magma becomes. Basaltic magma, low in silica and high in iron and magnesium, flows easily, forming broad, gentle slopes like those of Hawaii's shield volcanoes. Andesitic magma contains more silica and gases. It builds tall stratovolcanoes such as those in the Andes or the Cascades. Rhyolitic magma, rich in silica and poor in iron, is so viscous that it can trap gases until the pressure bursts outward in explosive eruptions, the kind that create vast calderas. Temperature further controls the story. Hotter magma, often exceeding 1100 degrees Celsius, remains fluid and releases gases gradually. Cooler magma, around 800 degrees, thickens as crystals grow within it, increasing resistance to flow. In these cooler melts, gases like water vapor and carbon dioxide have difficulty escaping, leading to sudden decompression when cracks open. The relationship between gas and melt behaves like that between steam and a kettle. If the lid is tight, the buildup becomes violent. The gas composition also defines the atmosphere around an eruption. Water vapor is always the most abundant, but carbon dioxide, sulfur dioxide, and traces of hydrogen chloride or fluorine can accompany it. These gases influence both human health and global climate. Sulfur dioxide combines with water droplets in the stratosphere to form aerosols that reflect sunlight, temporarily cooling the Earth. After major eruptions, sunsets glow red and distant regions experience cooler summers. Such effects remind us that volcanoes are not isolated phenomena, but actors in the planetary climate system. When magma nears the surface, physical and chemical processes accelerate, pressure drops sharply, gases expand, and crystals form rapidly as the liquid cools. The textures in solidified lava, glassy obsidian, porous pumice, or dense basalt record these transitions. In obsidian, cooling was so fast that atoms froze before they could form crystals. In pumice, gas bubbles expanded faster than they escaped, leaving a rock so light it can float on water. Basalt cooled more slowly, allowing minerals like pyroxene and olivine to grow visible crystals. Each texture is a snapshot of changing temperature and pressure, a frozen record of fluid behavior. Geochemists analyze these rocks to reconstruct the conditions deep below. Ratios of isotopes reveal the source materials in the mantle or crust. Trapped gas bubbles reveal the pressure at which they formed. By comparing samples from different eruptions, scientists can track how magma chambers evolve over time. They learn, for instance, that a single volcano may draw from multiple sources, a deep basaltic reservoir feeding a shallower, more evolved magma. The interaction between them can trigger renewed activity after years of quiet. Chemistry also shapes the colors of volcanic landscapes. Fresh basalt is dark gray or black, but exposure to oxygen and water weathers it into rust-red tones. Sulfur deposits near vents form yellow crusts. Minerals like copper and iron paint fumaroles in green and blue. Even the air glows differently as volcanic gases scatter sunlight. To an observer, these colors tell stories of temperature, oxidation, and time. The connection between chemistry and behavior makes volcanoes both predictable and endlessly variable. Scientists can identify patterns. Silica means viscosity. Viscosity means pressure. Yet each eruption still carries surprises. Minor differences in water content or ascent rate can shift outcomes dramatically. The planet's chemistry is precise, but its combinations are infinite. As you reflect on this, imagine magma as a living solution, its molecules rearranging with purpose but without thought. They respond only to the rules of physics, bonds forming, gases expanding, crystals aligning as heat escapes. This quiet obedience to law produces the spectacle we see at the surface. Fountains of fire that seem alive yet are simply chemistry revealing itself. In that realization there is peace. What feels chaotic is, at its root, the most orderly behavior nature can offer. So as you rest, think of that molten balance deep below, a dance of elements seeking equilibrium. The heat that once frightened early humans is also the reason life exists. The same volcano that destroys a valley releases the gases that build the air we breathe. Destruction and creation are not opposites here. They are stages of a single process, as predictable as cooling, as patient as stone. From the chemistry of magma arises the architecture of the volcano. Shape is not random. It is the visible outcome of pressure, temperature, and viscosity interacting over time. Just as a river sculpts its valley according to flow and sediment, molten rock sculpts the land according to how freely it moves and how often it returns. Every slope and crater is a record of the physical laws at work beneath our feet. The most graceful of these forms are shield volcanoes, broad, gently domed structures built from fluid basaltic lava. Each eruption sends rivers of molten rock sliding outward for many kilometers before they cool. Because the lava is thin and fast-moving, it spreads instead of piling high, creating slopes rarely steeper than a few degrees. The Hawaiian Islands are the classic example. Mauna Loa and Kilauea, immense mountains that rise from the sea floor yet appear smooth and calm from above. Their eruptions are frequent but usually non-explosive, glowing fountains of orange that illuminate the night without shattering the sky. By contrast, stratovolcanoes, also known as composite cones, are steep, layered, and dramatic. They form where thicker magma alternates between explosive and effusive phases, depositing beds of ash, pumice, and solid lava one atop another. Over centuries, this pattern builds elegant but unstable peaks such as Mount Fuji, Mount Rainier, and Mount Etna. Within their layers lie records of countless eruptions, each one sealing the memory of its heat beneath the next. When gas pressure becomes trapped within these tall cones, the release can be sudden and catastrophic. Entire summits can collapse, leaving craters that later fill with lakes or renewed flows of lava. Smaller still are cinder cones, simple piles of rock fragments ejected during brief bursts of gas-rich lava. The fragments fall close to the vent, forming steep slopes that erode quickly. These cones may rise within days or weeks and fade just as fast. They dot volcanic plains around the world, each a reminder that even fleeting activity leaves permanent marks. A fourth, more elusive form is the caldera, a vast depression formed when a large magma chamber empties and the surface above it collapses. Calderas can span tens of kilometers and hold entire ecosystems within their walls. Yellowstone in North America and Taupo in New Zealand are examples of these colossal structures. Their eruptions are rare on a human timescale, yet their impact reaches across continents. Ash from past caldera events has been found in sediments thousands of kilometers away, silent evidence of explosions so powerful they altered global climate for years. Each architecture reflects a dialogue between energy and restraint. The shield volcano releases steadily. The stratovolcano alternates between tension and release. The cinder cone spends its strength quickly, and the caldera stores its fury for ages before yielding. Scientists read these structures as outcomes of viscosity, gas content, and eruption rate, but one can also read them as metaphors for the balance of pressure in any system, how steady flow prevents collapse, how confinement breeds intensity, how release restores equilibrium. To build a mountain of fire requires more patience than fury. Each eruption adds only a thin layer. Lava that cools on the surface may insulate the flow beneath, allowing it to travel farther. With time, these layers accumulate into towering forms that seem eternal, though they too will weather and erode. Rain, wind, and frost grind them down, recycling the minerals into rivers and soils. Creation and erosion proceed together, partners in the same slow rhythm. When volcanologists model these systems, they do more than predict eruptions. They trace how material properties influence form. Laboratory experiments melt rock samples under controlled conditions, measuring how viscosity changes with temperature and pressure. Computer simulations then reproduce flows across digital landscapes, allowing scientists to forecast where lava will travel or where ash will fall. These tools translate physics into practical guidance, maps for evacuation routes, hazard zones, and long-term planning for communities living near volcanoes. In the stillness of this moment, imagine the planet shaping these architectures without haste. Picture a stream of lava hardening into black rock, another layer added to an ancient cone. Dust settles, rain falls, plants begin to grow. The same pattern repeats again and again, until the mountain stands as both witness and participant in Earth's endless cycle of renewal. As you breathe, notice how the rise and fall of your chest mirrors this pattern. Each inhalation builds pressure. Each exhalation releases it. The body, like the planet, maintains form through balance. The volcano, for all its power, follows the same principle. Its grandeur is not a product of violence, but of continuity, heat moving, cooling, solidifying, eroding, and returning once more to motion. Rest with that thought. Beneath the surface of continents and oceans alike, thousands of these architectures continue their work in silence. The planet keeps building, not to destroy, but to stay alive. When a volcano finally erupts, the quiet processes of pressure and chemistry reveal their strength in a single, visible act. Magma that has traveled for centuries through solid rock meets the open air, and the meeting transforms it instantly. What had been liquid becomes gas, ash, and light, spreading across the sky with force that can be heard hundreds of kilometers away. In that moment, the Earth vents its interior, connecting depths of darkness with the thin blue layer of atmosphere above. An eruption begins with acceleration. Gas expands within the rising magma, fragmenting it into droplets that freeze into tiny glass shards called ash. These particles, along with pumice, rock fragments, and steam, are thrust upward in a column that can climb 20 kilometers or more into the stratosphere. Within seconds, the eruption cloud cools and begins to spread laterally, forming the classic umbrella shape familiar from satellite images. The colors change from orange at the vent to gray, then white as the plume mixes with air and condenses water vapor. Lightning flickers through the ash, a byproduct of static charge built as particles collide. It is both beautiful and dangerous, the atmosphere's brief reply to the planet's deep exhale. Each eruption follows its own sequence of events. Some begin with explosive bursts and end with calm lava flows. Others open quietly and later escalate when gas-rich pockets rise through the conduit. The pattern depends on the interplay of pressure, viscosity, and the strength of surrounding rock. Volcanologists categorize eruptions by style: Hawaiian eruptions with fountains of lava, Strombolian with rhythmic bursts, Vulcanian with cannon-like explosions, and Plinian with towering columns of ash and pumice that can obscure the sun. These names, drawn from myth and observation, are less about classification and more about recognizing behavior. They remind us that nature repeats patterns, not exact events. The atmosphere itself becomes part of the eruption's machinery. As the hot plume rises, it entrains air, creating turbulent vortices that feed the column from below. At the same time, heavier fragments fall back around the vent, forming pyroclastic flows, fast-moving clouds of ash, gas, and rock that sweep down slopes at speeds exceeding 100 kilometers per hour. These flows are the most lethal part of explosive eruptions, capable of flattening forests and burying towns. Yet they also shape the landscape in creative ways, filling valleys with fertile new soil and sealing layers that will one day be studied as time capsules of the event. Scientists watch these moments with both awe and precision. Instruments record seismic activity, infrared cameras map heat signatures, and drones capture the geometry of ash plumes in real time. By comparing data across eruptions, patterns emerge that help forecast future behavior. The challenge is always scale. The same physical laws apply to small outbursts and massive ones, but their consequences differ by orders of magnitude. A minor vent can decorate a hillside. A major eruption can shift global climate. Ash clouds injected into the stratosphere reflect sunlight, sometimes lowering temperatures worldwide for months or even years. Historical accounts describe dimmed skies, cooler summers, and brilliant sunsets following major events. The particles that scatter light so beautifully are the same that disrupt air traffic and affect ecosystems. The sky becomes both witness and participant in the cycle of destruction and renewal. Even the sound of an eruption tells a story. Some are deep rumbles that carry through the ground. Others produce infrasound waves that travel around the planet, inaudible to human ears but measurable with sensitive instruments. Each frequency corresponds to energy released and the geometry of the vent. By studying these vibrations, scientists can estimate eruption size long before ash settles or lava cools. The planet speaks through physics, not words. For all its violence, an eruption is brief compared with the calm that surrounds it. Once the gas escapes and the pressure equalizes, the system quiets again. The column collapses, the lava cools, and new rock forms where there was once flame. The air clears, and rain begins to fall, washing ash into streams that carry nutrients across the landscape. Life will return faster than expected. Seeds buried beneath the debris will sprout in the enriched soil. In the cycle of geology, endings are beginnings waiting for time. If you listen now, you can imagine the echo of that release, fading into silence. The ground beneath your feet carries traces of ancient eruptions, layers compacted into the crust, waiting centuries to be seen again. Above them rest the calm of the present moment, air cool, sky clear, the memory of fire asleep beneath the surface. The earth is never truly still, but between its breaths lies peace. Throughout history, great eruptions have done more than sculpt the landscape. They have shaped civilizations, rewritten economies, and entered collective memory as symbols of both awe and fragility. Each eruption tells two stories, one written in ash and lava, the other in the lives it touches. Together they show that the planet's fiery breath does not stop at the horizon of science. It reaches deep into the human story. One of the earliest recorded disasters unfolded near the Bay of Naples in the 1st century of the Common Era, when Mount Vesuvius erupted with sudden violence. Columns of gas and ash rose high into the sky, collapsing roofs and burying entire towns beneath meters of pumice. Pompeii and Herculaneum vanished almost overnight, sealed away until their rediscovery many centuries later. Excavations reveal streets, frescoes, and bodies preserved at the moment of suffocation. For archaeologists, this tragedy became an unprecedented time capsule, evidence of Roman life frozen by the chemistry of an eruption. For humanity, it became a reminder of how swiftly the familiar can disappear. In the Indonesian archipelago, Krakatoa exploded in the 19th century with a force heard across half the globe. The blast sent shockwaves through the atmosphere, circling the Earth several times. A wall of water raced outward, erasing coastal towns, and global sunsets turned blood red for years. The eruption released enough material to cool the planet and inspired literature and art that tried to capture its scale. Modern atmospheric science traces some of its early ideas about aerosols and climate change to observations made after Krakatoa. Out of devastation came knowledge, born of careful measurement and the persistence to understand cause from chaos. Later, in the 20th century, Mount St. Helens reminded the modern world that volcanoes remain unpredictable even under observation. In the spring of 1980, weeks of tremors and visible swelling preceded a massive landslide and lateral blast. The eruption reduced the mountain's height by hundreds of meters, flattened forests, and filled valleys with debris. Yet the aftermath revealed something remarkable. Within months, green shoots returned. Biologists documented the recovery in detail, watching life reclaim the grey wasteland. Volcanic soil, newly exposed, became a laboratory for studying how ecosystems rebuild from nothing. It proved that even in destruction, the process of renewal begins immediately. Farther south, the eruption of Mount Pinatubo in the Philippines showed how local events connect to global systems. In 1991, satellites recorded a plume reaching the stratosphere, where it spread a veil of sulfate aerosols around the world. Average temperatures dipped, rainfall patterns shifted, and vivid sunsets painted the sky on every continent. Scientists used this data to refine models of climate sensitivity, confirming that even small changes in atmospheric particles can influence weather on a planetary scale. The eruption became a turning point for understanding the link between geology and climate science. These moments remind us that volcanoes are not isolated hazards. They are expressions of Earth's metabolism. Each eruption is a pulse, transferring heat, gases, and minerals from the interior to the surface. Humans have learned to read those pulses, to predict them, and sometimes to live alongside them with respect rather than fear. In Iceland, for instance, communities divert lava flows with barriers and cooling water. In Japan, dense networks of sensors feed real-time alerts to cities at risk. The knowledge gained from past catastrophes protects future generations. Science, in this sense, is memory organized into preparation. The psychological impact of eruptions endures long after the ash settles. Ancient cultures built myths to explain them, the anger of gods, the punishment of spirits, or the birth cries of creation. Modern minds may not personify the fire, yet the emotional response remains the same: humility before forces beyond control. Standing before a smoking crater, one feels both small and connected, aware that human history occupies only a moment in Earth's longer timeline. The ground beneath us is never truly still. It simply moves at a pace we rarely perceive. As you imagine these scenes tonight, Pompeii buried in silence, Krakatoa painting sunsets across the world, forests reborn around Mount St. Helens, let the thought settle that renewal follows every loss. The same heat that destroys also seeds life. The same dust that darkens skies later feeds the soil. The planet teaches resilience through repetition. It endures by continuing the cycle, by transforming its own violence into balance. Close your eyes to that rhythm. What seems like chaos is, in truth, an ancient conversation between the deep earth and the thin layer of life upon it. We remember these eruptions because they mirror the same patterns we feel within ourselves: pressure, release, and recovery. The world burns, cools, and breathes again. So do we. When a volcano's fury subsides, the world does not return to silence at once. The air still trembles with heat, rivers run thick with mud, and the landscape smoulders in shades of black and rust. What was once a forest may now be a plain of ash, dotted with fallen trunks and streams of steam. Yet beneath this devastation, renewal has already begun. The quiet after fire is not emptiness, it is preparation. In the days following an eruption, ash and dust settle like snowfall, sealing the ground under a thin crust of minerals. Rain mixes with these particles to form grey clay that traps moisture and nutrients. Within weeks, the first microbes arrive, carried by wind and water. They feed on the mineral-rich surface, transforming it into a thin film of living chemistry. From this humble beginning, the long recovery of the ecosystem unfolds. Scientists call this process primary succession, the birth of life on new ground. In Hawaii, mosses and ferns sprout on fresh lava only months after an eruption. In Iceland, glacial meltwater cools lava fields, leaving behind fertile plains where flowers bloom within a few seasons. Around Mount St. Helens, biologists documented the return of insects, birds, and plants in careful sequence, the arrival of spiders carried by silk threads in the wind, the nesting of small mammals, the growth of willows and alders along cooled riverbeds. Each step softens the scars of heat, each new root binds the soil and prepares it for the next generation of life. For the planet, these regrowth cycles are essential. Volcanic ash contains elements, phosphorus, potassium, magnesium, that enrich soil and feed vegetation. Erosion carries those nutrients into rivers and oceans, supporting plankton and marine ecosystems. Even the carbon dioxide released during eruptions contributes to maintaining Earth's temperature balance over geological time. The destructive phase and the regenerative phase are inseparable halves of one system. Fire clears, life returns. The human response follows a similar arc. Communities that lose homes to eruptions often rebuild on the same land. They return not out of denial but because the soil sustains them. Rice fields thrive on volcanic slopes in Java. Vineyards grow in the dark earth of Sicily. Coffee plantations flourish in Central America. Generations live with risk because the land rewards them with abundance. The volcano gives and takes, and people learn to live within that exchange. In the quiet that follows every eruption, scientists listen. Seismographs record faint aftershocks as magma chambers collapse and cool. The earth exhales its last gases through fumaroles that hiss softly for years. These sounds, too low for most ears, tell researchers how the interior relaxes after strain. In that slow unwinding, the planet finds balance again. What seems like rest is, in truth, the system stabilizing itself. There is a human parallel in that pattern, one that speaks directly to this moment. After intensity, there must be calm. After the pressure of thought, there must be release. The world teaches this without words. Even fire must rest. As you listen now, allow yourself to do the same. If sleep does not come quickly, let it arrive at its own pace. The ground beneath you has taken millions of years to cool, to steady, to become the surface you call home. You can take a few more moments to breathe. Picture a cooling lava field under the stars. The rocks still shimmer with faint warmth, but the air above them is calm. Steam rises in slow ribbons, twisting into the night until it fades into invisible air. The silence is deep enough to feel. Somewhere within it, the heartbeat of the planet slows, and the heat of the day gives way to the peace of darkness. This is what the end of an eruption sounds like. Not destruction, but recovery. When morning comes, that same landscape will glisten with dew, and seeds carried by the wind will settle into cracks. Life always waits at the edge of stillness. The volcano's quiet is temporary, but so is its rage. Both belong to a rhythm larger than either. The earth sleeps between breaths of fire, and in that sleep it gathers strength for what comes next. Tonight, you share that rhythm. The air around you cools, the pulse slows, and everything unnecessary begins to fall away. The planet rests beneath your feet, vast and alive, holding you in its calm. You can rest too. Most volcanoes on Earth never break the ocean's surface. Hidden beneath waves and darkness, they shape the planet more than all visible mountains combined. These submarine volcanoes form a continuous chain of ridges and peaks stretching across the seafloor, tracing the edges of tectonic plates. Together, they create a network so vast that it encircles the globe like a seam of glowing stitches. Here, fire and water meet not as enemies but as collaborators in the construction of new worlds. The mid-ocean ridges are where this process is most active. At these boundaries, molten rock rises through long fissures, cools rapidly, and solidifies into basaltic crust. The Atlantic, Pacific, and Indian Oceans each contain ridges thousands of kilometers long, where new seafloor is born every day. Though the motion is slow, barely a few centimeters per year, it is relentless. Over millions of years, this steady addition of material pushes continents apart, renewing the face of the planet. In this way, the Earth constantly rebuilds itself from the bottom up. Because water cools lava so quickly, submarine eruptions look different from those on land. When molten rock meets seawater, it quenches instantly, forming rounded shapes called pillow lavas. These smooth, bulbous forms pile atop one another like frozen bubbles. Inside each pillow, glassy surfaces and crystalline interiors record the sudden meeting of heat and cold. Scientists use remotely operated vehicles equipped with cameras and robotic arms to collect samples of these rocks. The data they gather, temperature, chemistry, mineral content, reveals the conditions deep below the crust. Around active vents, the sea comes alive with another kind of fire: hydrothermal systems. Superheated water, infused with dissolved minerals, gushes from cracks at temperatures exceeding 300 degrees Celsius. When it meets the cold ocean, metals precipitate out, forming towering chimneys known as black smokers or white smokers depending on their composition. These vents, rich in iron, sulfur, and copper, sustain entire ecosystems without sunlight. Microbes harness chemical energy from the vent fluids in a process called chemosynthesis, producing food that supports worms, crabs, and fish adapted to the darkness. This discovery, made in the late 20th century, changed our understanding of where life can exist, not only on Earth, but potentially on other worlds where light never reaches. The importance of submarine volcanism extends beyond biology. These undersea eruptions regulate the chemistry of the oceans, releasing elements that affect seawater composition and carbon cycles. The heat flux from the ridges influences deep ocean circulation, which in turn affects global climate. The seafloor is therefore not merely a passive surface, it is an active participant in planetary balance. Exploring these hidden landscapes is difficult. Pressure at depth crushes ordinary equipment, and visibility fades within meters. Scientists rely on sonar to map the terrain, converting echoes into three-dimensional images. The results reveal mountains taller than Everest and valleys deeper than the Grand Canyon, all concealed beneath kilometers of water. Volcanoes rise and collapse there unnoticed, their eruptions muffled by the sea. Yet each event adds new crust, building the foundation on which continents float. In these silent places, beauty takes an unfamiliar form. Imagine a dark plain lit only by faint blue light from mineral reactions. Clouds of shimmering particles drift like slow-motion snow. A vent opens, releasing a column of smoke that glows faintly as minerals crystallize in the water. It is a vision of creation in slow time, no sound, no sky, only motion and heat. The ocean floor, though unreachable to most, is where much of Earth's story is still being written. To think of volcanoes only as destructive mountains is to miss half of their identity. Beneath the sea they are patient builders, weaving new surface for continents to stand on. They work unseen, their rhythm measured not in eruptions but in the steady accumulation of stone. The calm they keep is the calm of persistence, the quiet labor of renewal. As you rest now, you might picture yourself drifting above those ridges, weightless in the dark water. Beneath you, molten rock rises and cools. Above you, the sea presses down with its soft, endless weight. The world feels still, yet creation continues everywhere. You need not see motion to know it exists. The planet is working even when it appears silent, and in that thought, perhaps you can find your own quiet continuation. Few places on Earth display the union of fire and ice as vividly as Iceland. Straddling the mid-Atlantic ridge, it sits directly above a rift where two tectonic plates diverge. Beneath its glaciers lies a hot spot, a plume of molten material that rises from deep in the mantle, feeding hundreds of active volcanoes. The island is young in geological terms, born entirely of eruptions over the last 20 million years. Here, the forces that build the planet are visible at the surface, raw and unmasked. To stand on Icelandic soil is to stand at the frontier of creation. The ground breathes steam through fissures. Rivers of melted ice run beside fields of black basalt. Geysers erupt rhythmically, their bursts of boiling water reaching the cold air with precision. Every feature tells a story of heat meeting cold, expansion meeting contraction. Scientists study this contrast to understand how magma interacts with ice and water, a relationship that shapes not only Iceland, but the evolution of the entire planet's climate and geology. When magma encounters ice, The results are dramatic. The heat melts the ice instantly, creating vast pockets of pressurized water beneath glaciers. These trapped lakes can burst without warning in sudden floods called eruptions. Entire valleys can be carved overnight, bridges swept away, and new channels etched into the landscape. Yet these same floods distribute sediment and nutrients that enrich plains downstream. The destruction that begins with fire ends with renewal in water. The interaction of lava and ice also creates unique rock formations. Rapid cooling forms glassy basalts filled with bubbles of frozen vapor. Pillow lavas and columnar joints, shaped by uneven contraction, form patterns that resemble sculptures carved by intention. Geologists examine these shapes to estimate cooling rates and eruption depths. They see in them the signature of processes that also occurred billions of years ago on a younger Earth, and perhaps on frozen moons beyond our planet, where similar conditions may exist. Iceland's geothermal energy is one of its greatest gifts. Wells tap directly into underground reservoirs of steam and hot water, turning turbines that generate electricity and heat homes. The entire nation thrives on this sustainable energy, living proof that volcanic heat can serve rather than threaten. In Reykjavik, warm water runs through pipes beneath city streets to keep them free of ice in winter, a quiet example of balance between human need and natural force. What once symbolized danger now provides comfort. The country's landscape changes with startling speed. In the late 20th century, the eruption of Eldfell on the island of Heimaey buried part of a fishing town under lava. Residents worked through the night, pumping seawater onto the advancing flow to cool it and divert its path. They succeeded. The harbor, nearly lost, became deeper and better protected. It was one of the rare moments when human ingenuity met geology on equal terms and prevailed through cooperation rather than resistance. Iceland also reminds scientists that glaciers and volcanoes are not separate phenomena but linked components of Earth's system. As climate warms and ice retreats, the pressure on the crust lessens. This reduction can increase volcanic activity, releasing more gases that further influence climate, a feedback loop both delicate and powerful. The planet constantly seeks equilibrium, adjusting through cycles of melting, eruption, and cooling. The study of Iceland offers clues to how these feedbacks shaped earlier epochs, including the end of ice ages and the renewal of ecosystems afterward. Visitors often describe Iceland as otherworldly, yet its landscapes are not alien at all. They are simply honest. They reveal what most of the planet hides, the direct interface between fire below and air above. The contrast of extremes creates a sense of calm in its logic. Nothing here is wasted. The steam that escapes from vents drives turbines. The lava that flows into valleys becomes new land. The ice that melts becomes river and sea. Destruction folds seamlessly into creation, visible for anyone who takes the time to look. As you settle into rest, imagine this balance, the slow meeting of opposites that defines both Iceland and the planet itself. Feel the warmth beneath the cold, the movement beneath stillness. Fire and ice do not fight. They coexist, shaping the world into harmony through tension. The same balance holds within you. Beneath calm, energy waits. Beneath energy, calm returns. The earth demonstrates this rhythm endlessly, and in understanding it, the mind can find its own equilibrium. Across the world's oceans, islands rise where fire meets water. Each begins as a rupture on the sea floor, a small vent exhaling lava into the cold darkness. Over time, layer upon layer of basalt builds upward until it pierces the surface and greets the air. The birth of an island is not an explosion, but a long, patient emergence. What begins in silence becomes a mountain surrounded by waves, a fragment of new land added to the planet's map. The Hawaiian archipelago is perhaps the most elegant example of this process. It sits far from any tectonic boundary, resting instead above a hot spot, a column of heat rising from deep within the mantle. As the Pacific plate drifts northwest over this stationary plume, volcanoes form in sequence. The oldest islands lie in the north, deeply eroded and covered in vegetation. The youngest, like the big island of Hawaii, remain active, their summits glowing at night with slow-moving rivers of lava. Each island marks a chapter in a moving story, one that spans millions of years and thousands of kilometers. Hotspot volcanism reveals much about the planet's interior. The plume's heat melts rock at its base, generating magma that rises through narrow conduits. When it reaches the surface, it spreads in thin basaltic flows, creating broad shield volcanoes with gentle slopes. The lava hardens into black rock, cracks, and weathers into fertile soil. Over time, ecosystems evolve in isolation, adapting uniquely to their volcanic homes. Hawaii's plants, birds, and insects are living evidence of geological patience translated into biological diversity. Elsewhere, similar plumes form chains of islands, the Galapagos in the Pacific, the Canaries in the Atlantic, and Réunion in the Indian Ocean. Each chain moves across its hotspot at a different speed, leaving behind trails of extinct volcanoes beneath the waves. Submarine mapping shows these drowned mountains, called seamounts, stretching like footprints across the ocean floor. Some may rise again if renewed by fresh magma. Others will erode into coral atolls, circles of reef that mark where fire once met air. Volcanic islands are laboratories of both geology and life. They allow scientists to study how ecosystems begin from nothing, how soil forms from rock, and how species evolve in isolation. The principles discovered there, adaptation, resilience, succession, mirror processes occurring on a planetary scale. Every island tells a condensed version of Earth's broader story: creation, erosion, and renewal. Humans have long been drawn to these islands despite their volatility. The same heat that forged them provides fertile ground for crops and minerals for trade. In Japan, Indonesia, and the Philippines, millions live on volcanic arcs, building cultures that celebrate both reverence and respect for the mountains that sustain them. Temples face volcanic peaks, myths describe them as the abodes of gods. The landscape teaches awareness, beauty entwined with risk, stability with impermanence. Some islands appear within a single human lifetime. In 1963, the sea southwest of Iceland erupted, giving birth to Surtsey. For several years, fountains of lava built a cone that broke through the waves, forming new land where none had existed. Scientists declared it a natural laboratory and restricted access to watch how life would begin. They observed wind-blown seeds taking root, seabirds nesting, and insects establishing colonies. Within decades, Surtsey had its first soil, its first grasses, its first ecosystem. The event showed that life requires only opportunity. Creation is always waiting for space to begin again. Every island, whether old or new, owes its existence to the same law, the upward reach of heat-seeking balance. Beneath each lies a conduit connecting it to the planet's deep interior. When that connection weakens, erosion takes over. Rain carves valleys, waves wear cliffs, coral builds along the coasts. The island ages gracefully, returning its material to the sea from which it came. Yet even as one island fades, another begins to rise somewhere else. The chain continues without pause. As you drift toward rest, imagine that slow emergence. In the dark ocean, pressure is immense and silence absolute. Then, a faint glow spreads upward, a plume of molten rock finding its path. It hardens, cools, and builds upon itself, grain by grain, wave by wave. Eventually, it breaks through the surface, touched by wind and sunlight for the first time. Steam rises, birds arrive, seeds take hold. Creation has completed another circle. The planet never stops building, and neither does life. Beneath the crust, heat continues its patient work. Magma stirs, gases rise, and the mantle circulates as it has for billions of years. From pole to pole, the planet maintains a slow, constant rhythm that never ceases. Volcanoes are its exhalations, the evidence that Earth remains alive inside. Even when the surface appears quiet, motion continues below. The crust flexes, shifts, and renews itself in cycles so vast that human time can barely measure them. To live on this planet is to share its restlessness. To understand it is to accept that true stillness does not exist. Volcanic systems follow patterns as old as the Earth itself. Heat escapes through weak points in the crust, forming vents and fissures that release gas, steam, and lava. When magma cools within these conduits, it creates new rock that seals the system until pressure builds again. Some volcanoes erupt often, others may wait tens of thousands of years. The long pauses do not mean death, but preparation. Deep within, minerals crystallize, gases accumulate, and chemical reactions reshape the magma chamber. Every volcano carries its own internal clock, ticking slowly toward equilibrium. Around the world, more than 1,500 active volcanoes remind scientists that the Earth's surface is still forming. Their activity spans a vast range, from the gentle flows of Kilauea to the explosive bursts of Mount Merapi. Many more lie underwater, unseen but no less vital to the planet's balance. Each eruption adds a layer to the crust, increases the ocean floor, or alters the atmosphere slightly. The sum of these actions maintains the dynamic stability that keeps the planet habitable. Without them, heat would accumulate below, and the surface would grow rigid and inert. The quiet exchange between interior and air is what allows life to persist. Geophysicists monitor this invisible motion using an array of tools. Seismic networks detect tremors before they reach the surface. Satellites measure small deformations in the ground. Drones collect gas samples near vents. From these signals, scientists infer the deep processes at work, transforming vibrations and light into understanding. The data tell a story of constant activity. Somewhere on Earth, magma is always rising, cooling, or finding new paths through the crust. The world breathes in molten rhythm. To the untrained eye, this continual movement might appear dangerous. Yet without it, the planet would lose the very qualities that sustain it. Volcanoes recycle the materials that make up continents and oceans. They bring carbon and sulfur to the surface, which eventually become part of the air and the sea. They create land, enrich soil, and influence weather. Their heat drives hydrothermal systems that support life even in the absence of sunlight. The same dynamic forces that can destroy also preserve a paradox at the center of geology's quiet grace. Humanity exists within this perpetual motion. Every breath you take contains traces of volcanic gases transformed through the ages, carbon dioxide exhaled by ancient eruptions, oxygen released by life that grew upon the soils they left behind. The connection between the inner earth and the outer world is complete, a loop that joins rock, air, water, and life in one unbroken cycle. Volcanoes are not anomalies but arteries of that system, moving energy and material between the planet's layers. As night deepens, imagine this vast mechanism continuing beneath your resting body. Beneath continents, magma rises slowly. Beneath oceans, new crust forms quietly. Even now, somewhere, an eruption lights the sky above a distant sea, while elsewhere a lava flow cools into stone. The earth never truly sleeps. Its calm is not stillness but balance, a harmony of forces working in opposite directions, always adjusting, never pausing. This is not something to fear, it is the assurance that life continues because the planet continues. You can mirror that same rhythm. Let the breath move without effort, in and out, a reflection of the world's own cycles. There is peace in motion when motion is understood. The steady processes beneath you do not disturb your rest. They sustain it. You are lying upon a living world, and that world, though it never stops, cradles you in constant balance. Every eruption is more than a spectacle of light and sound. It is a chemical conversation between the planet's interior and its surface. The reactions that unfold in molten rock define not only the character of volcanoes, but also the composition of Earth's crust, atmosphere, and oceans. Through chemistry, the deep Earth expresses itself, transforming raw elements into the building blocks of continents and life. The starting point lies in the minerals that make up the mantle, mainly olivine, pyroxene, and feldspar. When these minerals melt, they release oxygen, silicon, iron, magnesium, and trace elements such as nickel, chromium, and phosphorus. As the molten material rises, pressure decreases, changing how these atoms arrange themselves. Gases once dissolved in the liquid, water vapor, carbon dioxide, sulfur dioxide, separate and expand, fueling the power of eruptions. Each gas plays a distinct role. Water lowers viscosity, allowing magma to flow. Carbon dioxide drives explosive bursts. Sulfur dioxide cools the atmosphere when it reaches the upper air. In the balance of these ingredients lies the behavior of every volcano. Once the magma erupts and cools, it begins to crystallize. Minerals separate out of the melt according to their melting points in a sequence known as fractional crystallization. Early crystals, rich in iron and magnesium, sink to the bottom, while silica-rich liquids remain at the top. Over time, this process can change the composition of magma from basaltic to andesitic to rhyolitic. The Earth refines its own material through repeated cycles of heating and cooling, a kind of natural distillation that creates the diversity of igneous rocks we find across the planet. When volcanic gases meet the atmosphere, chemical transformations continue. Sulfur dioxide combines with water vapor to form droplets of sulfuric acid that scatter sunlight and reflect it back into space, creating temporary global cooling. Carbon dioxide, on the other hand, remains for centuries, contributing to the greenhouse effect that keeps the planet warm enough for liquid water. This interplay between cooling and warming has regulated climate for eons, long before humans learned to measure temperature. Without volcanoes releasing these gases, the atmosphere would have remained thin and sterile. With too many eruptions, the air could become choking and opaque. Balance, again, is the key. Volcanic rocks also feed the chemical cycles of oceans and soils. As rain weathers basalt, it releases calcium and magnesium, which react with atmospheric carbon dioxide and help store it in marine sediments. This process, known as chemical weathering, acts as a planetary thermostat, slowly regulating carbon levels over millions of years. In this sense, the cooling of lava is a silent environmental service, offsetting the warming caused by the gases released during eruption. The planet breathes through chemistry, exhaling carbon through fire, inhaling it through stone. Within lava lakes and fresh flows, remarkable reactions continue long after the surface has cooled. Iron oxidizes, giving the rock its deep red hue. Minerals align as they solidify, recording the direction of Earth's magnetic field. In these frozen records, geologists read reversals of polarity, plate movements, and even the timing of ancient eruptions. The chemistry of cooling rock becomes the memory of planetary motion. At hydrothermal vents, volcanic chemistry sustains entire ecosystems. Minerals leached from hot rock, iron, sulfur, and manganese, form the foundation of life that thrives without sunlight. Microbes convert these chemicals into energy through reactions similar to those that power living cells. Many scientists believe life itself may have begun in such environments, where volcanic heat, water, and chemistry intersected to produce the first self-replicating molecules. The same conditions that can erase life also have the power to create it. From this perspective, volcanoes are not mere features of geology but participants in biology. They provide nutrients, control gases, and maintain the temperature range in which ecosystems can flourish. Even extinction events linked to massive eruptions eventually lead to renewal, filling the world with new species adapted to altered climates. Fire resets the system so that life can reinvent itself. When you imagine volcanoes now, see beyond the eruption. Picture the invisible exchanges that follow, the gases dissolving into clouds, the minerals drifting through rivers, the new land slowly blending into the old. Every spark of creation carries a trace of chemistry that continues long after the flames have gone. The soil under your feet, the air in your lungs, the color of the oceans, all are echoes of reactions that began in molten depths. As you rest, allow that thought to steady you. The same chemistry that builds mountains also sustains your breath. You and the planet share the same elements, rearranged into different forms. The cycle of transformation never ends, yet its rhythm is calm and dependable. Let that continuity guide you towards stillness, the peace that comes from knowing that even in ceaseless change, there is enduring order. After every eruption, the earth cools slowly, releasing its heat into space. What remains beneath the crust is a slow burning glow, a reminder that the planet's heart is never fully at rest. The same heat that once created continents still seeps upward, inch by inch, molecule by molecule. It warms groundwater, drives tectonic motion, and fuels the quiet chemistry of stone. The volcano may sleep, but the planet does not. Beneath the silence, the pulse continues. When scientists speak of the Earth's thermal evolution, they refer to this gradual loss of primordial heat. Radioactive decay within the mantle still produces energy, but the rate has declined since the planet's formation. Over billions of years, the crust has thickened, slowing the escape of heat, yet never stopping it completely. Each eruption, each flow of lava, each small vent of gas is part of this cooling process. In geological terms, Earth is like an ember, glowing faintly after a long fire, still alive, still warm enough to sustain movement and life. The night side of the planet tells this story beautifully. Viewed from space, city lights outline continents, but beyond them, volcanoes shine with a subtler glow. Thermal cameras detect warm spots where magma lies close to the surface, an invisible constellation of heat scattered across the globe. From Etna to Kilauea, from the rift valleys of Africa to the arcs of the Pacific, each glow marks an active connection between the surface and the deep mantle. These are the Earth's night lights, ancient and patient, their flicker measured not in hours but in ages. Volcanoes are often described as destructive, yet their cooling phases are acts of restoration. As lava solidifies, it contracts, cracking into patterns that resemble geometry drawn by unseen hands. Rain begins to fall, carrying minerals into the sea. Rivers carve valleys through the still warm rock, and plants return to claim the ground. The heat that once seemed hostile becomes the very foundation for new ecosystems. On cooled volcanic slopes, forests of birch, oak, and pine take root. Moss covers lava fields like a living blanket. Life does not wait for stillness. It thrives on recovery. From a broader perspective, the cooling of Earth represents balance in its purest form. Too much heat, and the crust would remain molten. Too little, and tectonic activity would cease, leaving a barren, lifeless shell. Somewhere between those extremes lies the narrow zone where motion persists and life endures. Our planet has maintained that equilibrium for billions of years, cycling energy with remarkable precision. Volcanoes, in their rhythm of eruption and rest, embody this constant negotiation between excess and restraint. Humans, too, live by this balance. The same principles that guide the Earth's cooling govern the way bodies and minds find rest. After exertion comes release, after intensity, calm. Just as magma solidifies into stone, thoughts settle into silence. The warmth remains, but its form changes. Energy becomes structure, motion becomes stability. In this way, rest is not the absence of energy, it is its transformation. Tonight, let that transformation become your rhythm. Imagine yourself as part of the planet's long exhale, the heat beneath your feet, the cool air around you, the quiet between your breaths, all mirror the same cosmic balance. The Earth releases what it no longer needs, not in haste but in peace. You can do the same. Let each exhale carry away the pressure of the day as the planet releases its own heat through silent fissures in the crust. If sleep comes slowly, think of cooled lava under the stars, dark, solid, serene. Its journey from fire to stone is complete, yet traces of warmth linger inside, hidden and steady. That is how rest begins. Warmth enclosed within stillness, motion turned inward until it becomes calm. The world does not demand silence, it finds it naturally as temperature falls, as energy becomes order. The long night of the Earth is not a pause but a continuation. Beneath its surface, cycles persist, quiet but faithful. So too within you, breath follows breath, heart follows rhythm. The same physics that cools a planet guides your own recovery. You are, for this moment, aligned with a world that never truly sleeps, only breathes more softly in the dark. When a volcano quiets, its work is not over. The surface may appear barren, but within weeks of cooling, life begins its cautious return. What seems desolate becomes a frontier of renewal. The world starts again, grain by grain, cell by cell, following the same patient laws that guide every recovery since the planet's beginning. The first pioneers are often invisible. Wind and rain deposit dust, spores, and microorganisms onto the still warm rock. Bacteria and cyanobacteria settle into cracks, forming microscopic colonies that capture sunlight and carbon dioxide. They generate thin films of organic matter, precursors to soil. Lichens follow, their partnership between fungi and algae, creating acids that slowly break down mineral surfaces. Over years, their combined activity begins to crumble basalt into grains fine enough to hold water. It is the quietest form of construction imaginable, a city of life built from chemistry and patience. When mosses arrive, they take advantage of this primitive soil. Their root-like structures, called rhizoids, bind particles together and trap moisture. As they die and decay, they add new organic material, thickening the fertile layer. Seeds carried by wind or birds find a place to rest. Grasses sprout, followed by shrubs and eventually trees. In a few decades, a wasteland can transform into a forest. The soil that supports it is, in essence, recycled volcano, rock turned to life, life turned back to rock in endless exchange. Biologists who study these successions describe them as nature's experiments in time. The process demonstrates resilience as a rule, not an exception. On Mount Street, Helens, scientists documented how pocket gophers, burrowing mammals, accelerated regrowth by turning over ash and exposing nutrient-rich layers below. Each species played a role, often unknowingly, in speeding recovery. The lesson was clear: disturbance and healing are not opposites but sequential partners in the same cycle. In tropical regions, recovery happens even faster. On Java and Bali, rice farmers cultivate fields on volcanic slopes that erupted within living memory. The ash that once buried villages now yields abundant harvests. Minerals in the soil provide constant fertility, eliminating the need for artificial fertilizers. These landscapes embody a paradox that has shaped human life for millennia: the willingness to live beside danger for the sake of abundance. The very ground that threatens also sustains. From a planetary perspective, this exchange is part of Earth's larger metabolism. Volcanoes release gases that enrich the atmosphere, while plants absorb those gases and store them in wood and soil. The carbon that leaves through fire returns through photosynthesis. In this way, the cycles of geology and biology intertwine, ensuring balance between energy and matter. Every leaf owes its existence to some ancient eruption, and every rock contains remnants of past life transformed by heat. The distinction between living and non-living matter blurs at the edges. Even the oceans participate in this renewal. Volcanic islands surrounded by water attract seabirds, which bring nutrients from distant feeding grounds. Their droppings add nitrogen to the soil, stimulating rapid growth. Coral reefs often form around the submerged edges of extinct volcanoes, turning stone into habitat for fish and algae. Life expands wherever stability follows chaos. The pattern repeats on every scale, from microbes colonizing ash to continents reshaped by tectonics. Standing on a cooled lava field years after an eruption, one can feel both the enormity and the tenderness of this process. Beneath your feet, basalt still holds traces of warmth, yet tiny plants cling to it, defying the odds. Each sprout, each blade of grass, each drop of dew marks a victory of persistence over destruction. There is nothing miraculous about it. It is simply the natural result of conditions aligned for renewal. The earth does not need to plan its healing. It follows the rules written into its chemistry and sunlight. For those who live in the shadow of volcanoes, this truth offers comfort. What is lost will return, changed but not erased. The planet is skilled at rebuilding. So too are we. After hardship comes adaptation, and through adaptation, growth. The lessons of the land echo in human resilience. As you rest now, imagine those tiny green shoots spreading over dark rock, reclaiming the landscape inch by inch. The wind carries seeds as softly as your breath moves in and out. Life does not rush, it simply continues. The same rhythm that renews forests after fire can restore calm after turmoil. The volcano cools, the field blooms, the heart steadies. Everything finds its balance in time. Long before life appeared, volcanoes were already shaping the air itself. The first atmosphere that surrounded the young Earth was thin, unstable, and quickly stripped away by the solar wind. What replaced it came not from above but from below, from countless eruptions that released the gases trapped within the planet's molten body. Every exhalation of fire was a contribution to the air we breathe today. Early in Earth's history, when the crust was still forming and impacts from space were frequent, volcanoes vented massive amounts of water vapor, carbon dioxide, nitrogen, and traces of methane and ammonia. As the planet cooled, the water vapor condensed to form oceans. Carbon dioxide dissolved into those oceans, reacting with minerals to create carbonate rocks. Nitrogen, inert and stable, accumulated in the atmosphere, becoming its main component. In this way, the balance of gases that makes life possible originated from geologic breathing. Volcanoes did not merely build the continents, they built the sky. Scientists study ancient lava flows and trapped gas bubbles to reconstruct the composition of this early air. Each bubble acts as a microscopic time capsule, preserving the chemistry of the planet's youth. The evidence shows that volcanic activity played a central role in maintaining temperature and pressure at levels where liquid water could persist. Without continuous outgassing, the Earth might have frozen into a silent, lifeless world. Too much outgassing, and it might have turned into a furnace like Venus. The planet walked a narrow path between extremes, guided by cycles of eruption and cooling. Over eons, volcanic gases created the conditions for biology to arise. Lightning in the early atmosphere likely interacted with these gases to form organic molecules, amino acids, and other carbon-based compounds. In warm volcanic pools and submarine vents, these molecules concentrated and combined, forming the precursors of life. Modern experiments have recreated similar reactions, confirming that heat, minerals, and gas can together produce complexity. Life, it seems, began not in tranquil gardens but in the dynamic interplay of fire and water. Even after the first organisms appeared, volcanoes continued to shape evolution. Periods of intense activity injected sulfur and carbon dioxide into the air, altering climate and driving adaptation. Massive volcanic provinces known as flood basalts poured over continents, triggering extinctions that opened the way for new species. The planet's atmosphere evolved in partnership with its geology, each influencing the other through feedback loops that continue to this day. In the present era, volcanic emissions remain small compared to human industrial output, yet their role is still vital. They replenish trace gases, provide nutrients through ash deposition, and influence cloud formation. On geological timescales, volcanoes remain the lungs of the planet, regulating the slow exchange of carbon between the deep interior and the surface environment. The term outgassing may sound mechanical, but it describes a kind of respiration, the planet exhaling to maintain equilibrium. To imagine this process, think of a deep breath drawn by the Earth itself. Magma rises, carrying dissolved gases much like blood carries oxygen. When the pressure drops near the surface, the gases escape, expanding into bubbles and then into the open air. The planet breathes out water vapor that becomes rain, carbon dioxide that feeds plants, and sulfur that eventually returns to rock. The cycle completes itself in endless repetition. What begins as mineral ends as atmosphere. What begins as air returns as stone. The next time you feel the wind, you are feeling the legacy of those ancient exhalations. Every breeze carries molecules once imprisoned in magma. The nitrogen you inhale was born from the planet's earliest eruptions. The water in your body was once steam rising from molten rock. Even the oxygen you breathe exists because volcanoes helped sustain the chain of reactions that allowed plants to evolve and fill the sky with life. In every breath, there is a trace of fire. As you close your eyes tonight, let that idea expand quietly inside you. The air around you is ancient, shaped by cycles so vast that they defy imagination. Each inhalation connects you to the deep time of the planet, to eruptions long vanished but never forgotten. The atmosphere is not separate from the Earth, it is the Earth, extended and transformed. Just as volcanoes breathe to maintain their balance, you breathe to maintain yours. The rhythm is the same, the purpose identical, to sustain life through motion and release. The story of volcanoes does not belong to Earth alone. Across the solar system, worlds both large and small bear marks of internal fire. Some erupted long ago and then fell silent. Others still burn, releasing heat into the cold vacuum of space. These distant volcanoes reveal what happens when the same natural laws meet different conditions, how gravity, pressure, and chemistry shape landscapes across the cosmos. On Mars, volcanic activity once sculpted a planet of immense proportions. The giant shield volcano Olympus Mons rises nearly 25 kilometers above its surrounding plains, making it the tallest known mountain in the solar system. Its size is possible because Mars lacks plate tectonics. On Earth, a hot spot moves relative to shifting plates, creating island chains. On Mars, the crust remains fixed, allowing magma to build layer upon layer in one location for millions of years. The result is a mountain so broad that its base could cover an entire country. Though Olympus Mons is no longer active, the network of fissures, calderas, and lava plains around it preserves evidence of ancient flows. They speak of a time when the planet's core was warmer, when its interior still pulsed with enough heat to reshape its surface. Further south, a region known as Tharsis Rise contains several smaller volcanoes, Ascraeus, Pavonis, and Arsia Mons, each aligned like steps across the red planet. Together they form a plateau thousands of kilometers wide. Scientists believe the Tharsis province once released so much gas that it altered Mars's atmosphere, thickening it enough to support liquid water on the surface. In a sense, Martian volcanoes may have created the conditions for the planet's brief, wet era before the atmosphere thinned again and the surface froze. Even now, orbiters detect faint signs of residual heat below some regions, suggesting that Mars's volcanic heart has not completely cooled. Where Mars reveals a memory of fire, Venus may still hold active flames. Beneath its dense clouds of carbon dioxide, radar mapping has shown circular domes, lava flows, and deformed plains resembling those of Earth's volcanic fields. Some of these surfaces appear remarkably young, less than a few 100,000 years old. Infrared sensors aboard orbiters have detected transient bright spots that could indicate ongoing eruptions. If confirmed, Venus would join Earth and Jupiter's moon Io as the only bodies with known active volcanism today. The difference lies in their energy source. On Venus, the thick atmosphere traps heat through an extreme greenhouse effect. Surface temperatures exceed 400 degrees Celsius, keeping the crust soft and mobile. This allows magma to rise more easily than on colder planets. The result is a landscape of sprawling volcanic plains and broad shield structures rather than tall cones. The air itself, filled with sulfur dioxide, echoes the chemistry of continuous outgassing, a planet in perpetual fever. The most violent volcanic activity in the solar system, however, belongs to Io, one of Jupiter's largest moons. There, tidal forces from Jupiter's immense gravity flex the moon's interior, generating heat through friction. The energy is so intense that hundreds of active volcanoes cover its surface, some ejecting plumes of sulfur that rise hundreds of kilometers high. The moon's surface constantly renews itself, painting patterns of yellow, white, and red as sulfur compounds cool and crystallize. Spacecraft passing by have photographed fountains of molten rock erupting into the blackness of space, a spectacle that demonstrates that volcanic power is not limited to large planets, but can thrive wherever energy is confined and seeking release. These worlds, so different in temperature and atmosphere, reveal a shared principle. Volcanism is the universe's method of transformation. It redistributes heat, reshapes surfaces, and cycles materials from interior to exterior. Whether beneath oceans or within alien skies, the same logic applies. Pressure accumulates, cracks open, energy escapes, and balance returns. Earth's volcanoes are one expression of this universal process. To study them is to glimpse the inner workings of worlds beyond our own. Imagine looking up at the night sky and knowing that somewhere on another world, molten rock is spilling into alien air. The glow would be unseen to human eyes, but the principle is identical. Heat, rising, cooling, solidifying. Across the vastness of space, planets and moons breathe through fire. Each eruption, no matter how distant, is part of the same cosmic rhythm that began with the first spark of creation. Not all volcanoes burn with molten rock. On distant, frozen worlds, eruptions take a different form, one ruled not by fire but by ice. These are the cryovolcanoes, fountains of water, ammonia, and methane that behave like lava under conditions of extreme cold. They blur the line between what is familiar and what is alien, showing that the language of volcanism extends far beyond heat. Where the sun's warmth fades, other forms of energy take its place, reshaping icy moons with quiet eruptions in the dark. Among these worlds, Io, the innermost large moon of Jupiter, stands apart as a paradox. While most outer moons are frozen, Io is alive with molten sulfur and silicate lava. Its energy comes from tidal friction, gravitational stretching caused by Jupiter and neighboring moons Europa and Ganymede. This constant flexing generates more heat than radioactive decay ever could. The result is a world in perpetual eruption, its surface resurfaced every few years. Observations from spacecraft have revealed glowing lava lakes, volcanic plumes rising hundreds of kilometers high, and rivers of molten sulfur flowing across plains of frost. Io demonstrates that volcanism needs only energy and material, not sunlight, to thrive. Move outward from Jupiter, and a transformation begins. On Europa, the same tidal forces act through a thick shell of ice rather than rock. Beneath that shell lies a global ocean of salt water. When heat from below fractures the ice, jets of water vapor escape into space. These plumes resemble miniature volcanoes, their eruptions driven by pressure and expansion rather than combustion. Scientists have detected traces of organic molecules in these emissions, sparking interest in Europa as a potential cradle for life. Beneath its frozen crust, chemical reactions between water and rock could produce energy sources similar to those at Earth's hydrothermal vents. In this way, volcanic activity, whether fiery or frozen, remains a companion to the possibility of life. Beyond Europa lies Enceladus, a smaller moon of Saturn, whose south pole gleams with icy fountains visible from orbit. The moon's surface fractures into tiger-striped ridges, where geysers of vapor and ice crystals erupt continuously. These plumes feed Saturn's faint E-ring, scattering snow into space. Beneath the surface, scientists believe, lies a warm ocean kept liquid by the same tidal heating that powers Io's molten fires. Samples of the plumes analyzed by passing spacecraft reveal salts and complex organic compounds, signs of active chemistry. Here, the concept of volcanism expands again. Eruptions of water rather than magma, creating snow instead of lava, yet following the same universal pattern of energy, release, and renewal. Even farther out, on Neptune's moon Triton and dwarf planet Pluto, geysers of nitrogen gas burst through layers of frost. Sunlight and internal heat combine to pressurize volatile ices until they vent explosively, leaving dark streaks on the surface. These distant outbursts last only moments but reshape the terrain over time, reminding scientists that volcanism is not a singular phenomenon but a spectrum of behaviors unified by physics. Wherever material can melt and refreeze, volcanism, of some form, will exist. Cryovolcanoes alter the way scientists define habitability. On worlds once dismissed as frozen dead, these eruptions circulate chemicals, create gradients of temperature, and move energy through otherwise static environments. In these gradients, life may find footholds. The same principle applies everywhere. Dynamic systems foster complexity, and complexity opens the door to living processes. The study of icy volcanism has therefore become one of the most hopeful fields in planetary science, linking the mystery of geology to the search for life beyond Earth. There is something quietly poetic in the idea that even in the farthest cold, something still moves and breathes. Where sunlight cannot reach, heat still rises from within, shaped by gravity's pull and matter's persistence. The frozen moons of the outer solar system remind us that rest and motion coexist in every corner of the universe. What we call silence is merely activity too slow or too subtle for the senses. As you picture these distant worlds, imagine plumes of vapor drifting into the starlit void, each a whisper from a hidden ocean, each a sign that warmth endures in the coldest places. The cosmos, like the Earth, is never still. Its rhythm continues far beyond what eyes can see, in tides of rock, ice, and vapor. Even at the edge of darkness, creation does not sleep, it simply changes form. Beyond our solar system, volcanoes may shape the faces of worlds we have never seen. Astronomers call them exoplanets, planets orbiting distant stars, each with its own chemistry and heat. Though no telescope has yet captured an eruption directly, traces of volcanic activity appear in their atmospheres, written in gases that betray an inner fire. To search for volcanoes on other worlds is to look for signs of movement, evidence that they, too, are alive within. The most likely candidates are rocky planets orbiting close to their suns. These worlds experience strong tidal forces, similar to those that heat Jupiter's moon Io. The constant gravitational pull stretches their interiors, generating friction and molten rock. When that heat rises to the surface, it releases gases that can be detected from light years away. Telescopes studying starlight passing through exoplanetary atmospheres sometimes find spectral signatures of sulfur dioxide, carbon monoxide, or silicate dust, chemicals linked to volcanic activity. Each detection is a faint echo of processes familiar to us: magma rising, gas expanding, crust reshaping. One world in particular, called 55 Cancri E, may be an extreme example. It orbits so close to its star that a year lasts less than 2 Earth days. Its surface temperature exceeds 2000 degrees Celsius, hot enough to keep rock in a molten state. Observations show periodic changes in infrared brightness, suggesting that flows of lava cover its day side and then cool as the planet rotates. If confirmed, it would be a world where volcanism never ceases, a constant ocean of molten stone illuminated by eternal sunrise. Such planets teach scientists what happens when volcanic processes occur at temperatures far beyond Earth's range. Volcanism may also play a crucial role in planetary habitability. For life to exist, a planet must recycle gases, maintain surface temperature, and sustain chemical diversity. On Earth, volcanoes release carbon dioxide that warms the atmosphere, countering the cooling effects of weathering and ice formation. Without that greenhouse balance, the oceans would freeze solid. A similar balance might determine whether distant planets remain habitable. Too little volcanism, and they turn cold and inert. Too much, and they become infernos. Somewhere between lies the narrow zone where stability supports life. Scientists model this balance by comparing planets of different sizes and compositions. Small planets cool quickly and lose internal heat, becoming geologically dead. Large planets retain heat longer, but their gravity may trap gases so tightly that eruptions never break the surface. The sweet spot lies with worlds like Earth, massive enough to hold energy, but thin-skinned enough to let it escape. The pattern is mathematical yet elegant. Habitability is not an accident, but a consequence of physical harmony between heat, mass, and time. To detect volcanism across light years requires creative methods. Astronomers analyze starlight filtering through a planet's atmosphere during transit. Tiny differences in brightness at specific wavelengths reveal chemical fingerprints. When sulfur dioxide or sodium vapor appears temporarily and then fades, it hints at episodic eruptions. Other clues come from temperature variations measured in infrared light, showing regions that heat and cool cyclically. These faint signals are the cosmic equivalent of distant smoke on the horizon. Each discovery brings us closer to confirming that volcanic activity is not rare but universal. If volcanic activity shapes other planets as it does ours, then the universe must be filled with worlds continually remade by internal heat. Continents rise and fall, skies thicken and clear, oceans form and evaporate. On some, the process may create atmospheres rich enough to nurture biology. On others, it may strip them bare. But in every case, volcanism remains a creative force, ensuring that planets evolve rather than remain static. It is the signature of worlds that are still becoming. When you look up at the stars, remember that behind those distant lights are landscapes as restless as ours. Some are wrapped in ice, others in fire, yet all follow the same principles of physics. Heat moves toward cold, pressure seeks release, matter circulates in endless cycles. The universe breathes through its volcanoes, from the smallest moon to the brightest planet. Creation, it seems, is not a single event, but a continuous act carried forward by energy and time. As you rest, let that image widen your sense of calm. You lie on one planet among countless others, each turning slowly, each alive in its own way. Somewhere in that infinite distance, a volcano may be erupting beneath an alien sky, casting light across a frozen plain. Its glow will fade, its heat will cool, but the rhythm continues, the shared heartbeat of worlds still forming. Every volcano, no matter how fierce its eruptions, eventually quiets. Its magma chamber empties, the vents seal, and the slopes erode into gentler forms. The mountain remains, but the fire within grows still. This stage, dormancy, is not an ending. It is a pause in a much longer rhythm, the steady breath of a planet that alternates between creation and rest. A dormant volcano may sleep for centuries or even millennia. Beneath its surface, magma cools slowly, forming solid rock and releasing the last gases through thin cracks. Geologists monitor such mountains carefully, searching for subtle signs of reawakening. A rise in ground temperature, faint tremors, new springs releasing sulfuric vapor. These hints show that the system below is never completely silent. The Earth, like a living organism, keeps a heartbeat beneath its calm exterior. The shape of a dormant volcano changes with time. Wind and rain sculpt its flanks, rivers carve valleys, and vegetation takes hold. In these transformations, the landscape softens, merging with the rhythms of life it once disrupted. Layers of ash become soil, fertile and dark. Forests grow over lava fields, and animals return to graze on grass rooted in once molten stone. The fire that destroyed becomes the foundation that sustains. Dormancy, then, is both recovery and renewal, a demonstration that even the fiercest energy seeks balance in the end. Some volcanoes never awaken again. When their magma source cools or shifts away, they become extinct, monuments to an earlier age of activity. Mount Kilimanjaro, Mount Kenya, and Mount Taylor are examples of this quiet permanence, mountains that stand as memories of a hotter Earth. To scientists, these extinct giants are archives of geological history. Their layers reveal how chemistry, climate, and erosion have changed through time. They are textbooks written in stone, patient and exacting, offering clues about how planets evolve and stabilize. Dormancy also carries an element of mystery. No one can predict precisely when a volcano will reawaken. Decades or centuries of silence may pass, and then, suddenly, a subtle tremor deep below signals the return of movement. Pressure builds, fractures widen, and the cycle begins again. The unpredictability of these events reminds us that stillness is never absolute. Beneath even the quietest landscapes, change waits. The lesson is humility. Control is an illusion, but understanding is possible. From a broader view, this state of dormancy mirrors the cycles of our own lives. Intensity alternates with rest, effort with renewal. The mind, like the mantle, must cool to regain strength. Creativity, emotion, and thought all follow patterns of eruption and pause. Too much activity leads to exhaustion, too little to stagnation. Balance arises only through rhythm, through allowing both motion and stillness to have their time. Volcanoes teach this silently, through their long intervals of patience. As you breathe now, you share that same rhythm. The air moves in and out, like tides within the body. There is no need to force stillness. It arrives on its own when heat has done its work. If sleep does not come immediately, let it gather slowly, as magma gathers strength deep below. Rest, like lava, flows when it is ready. It fills the spaces that need renewal and leaves behind the calm structures that sustain you through the next cycle. Picture a volcano under starlight, its slopes dark, its summit quiet. Mist curls around the crater, and the wind moves through grass growing on ancient rock. Inside, warmth lingers but does not rise. The earth holds its breath, neither restless nor empty, simply balanced. This is not the absence of life, but the proof of endurance. The mountain has nothing to prove. It waits, unhurried, as time moves gently around it. In that same patience, you can find your rest. The energy within you does not vanish. It changes form. It cools, settles, and becomes steady. The planet beneath you sleeps lightly, and so can you, warm at the core, calm at the surface, part of the same long rhythm of renewal that has carried the world for billions of years. Volcanoes are often seen as isolated mountains, but in truth, they are the masons of the continents. Every grain of sand, every fertile plain, every ridge and plateau owes something to volcanic construction. Over geological time, their eruptions have raised islands, expanded coastlines, and shaped entire land masses. The solid ground beneath our feet is, in large part, the cooled residue of ancient fire. The continents we know today began as fragments of volcanic crust. In Earth's early history, the surface was thinner, the heat more intense, and magma flowed freely through vast fissures. As it cooled, lighter rocks such as granite accumulated, floating on denser basaltic material beneath. Over time, these fragments collided and merged through tectonic motion, forming the first stable continental cores, known as cratons. Volcanic arcs along subduction zones, where one plate dives beneath another, continued to add layers of new material, welding islands, and sediments into larger structures. Every mountain range carries this legacy of assembly through heat. Modern geologists can trace the lineage of continents by studying the isotopic fingerprints of their rocks. They find evidence of volcanic recycling everywhere. Ancient lava flows, metamorphosed by pressure, become the granite foundations of mountain chains. Basaltic plateaus that once formed beneath oceans are uplifted to form highlands. Even the deep roots of continental shields show signatures of partial melting and refreezing, proof that continents are not static, but continuously remade by volcanism working in slow motion. One of the most dramatic examples of this process can be found in the Pacific Ring of Fire, a vast horseshoe-shaped zone encircling the ocean. Here, subduction creates lines of volcanoes stretching from the Andes to Alaska, from Japan to New Zealand. These volcanic arcs act as both destroyers and builders. They consume oceanic crust while creating new continental rock. In the Andes, eruptions over millions of years have raised mountains, several kilometers high, and extended the South American landmass westward. The same pattern unfolds in countless other regions, where eruptions beneath the sea slowly give rise to islands, which later merge into continents through tectonic drift. Volcanoes also influence the vertical balance of the Earth's crust through a process called isostasy. When mountains build up through eruptions, their weight pushes the crust downward, like ice floating deeper into water as it thickens. Erosion then wears the surface away, reducing pressure and allowing the crust to rise again. This constant interplay between building and leveling keeps the planet's surface in equilibrium. Even as volcanoes create height, gravity and time restore balance, ensuring that no structure lasts forever. In another sense, volcanoes are the engineers of habitability. By continually replenishing the surface with minerals and gases, they maintain the carbon silicate cycle that regulates climate. Weathering of volcanic rocks removes carbon dioxide from the air, while new eruptions return it. This steady exchange has kept Earth's temperature within a range suitable for life over billions of years, despite fluctuations in solar output. Without this slow feedback, the planet would have long since frozen or overheated. Continents, oceans, and life itself exist because volcanism never stops completely, it only changes tempo. On the timescale of human existence, these processes seem invisible. Mountains rise and erode too slowly for the eye to see. Yet their consequences are everywhere. Fertile valleys, mineral deposits, geothermal energy, even the air we breathe. Every civilization rests on ground forged by fire. Cities built on volcanic plains, Naples, Tokyo, Quito, Mexico City, stand both in gratitude and in risk. The soil that feeds them is the same that might one day shift beneath them. This duality defines humanity's relationship with volcanoes, fear and dependence intertwined. To grasp this paradox is to understand that stability is built on motion. The continents themselves float, drift, and evolve, and yet they provide the illusion of permanence. The Earth offers solidity not because it is still, but because its movements are measured across deep time. Volcanoes, the architects of continents, teach us that endurance does not mean immobility, it means adaptation through change. As you think of this tonight, picture the world beneath its thin crust. Rivers of magma move slowly, invisible but essential, carrying the ingredients of future landscapes. Every mountain you have seen, every plain you have crossed, began as molten stone rising through darkness. The continents are not finished creations, but ongoing works of balance, foundations that cool and shift yet hold us steady. In that understanding, there is calm, the comfort of knowing that what endures does so by quietly renewing itself, again and again. Beneath every mountain, every forest and ocean, the planet continues to move. The deep mantle circulates in slow waves of heat, each one lasting millions of years. This movement is the hidden heartbeat of Earth, steady, unhurried, essential. Volcanoes are the points where that pulse touches the surface, where interior motion becomes visible for a moment before returning to quiet. They remind us that even in stillness, the world breathes. Scientists call this constant process mantle convection, but it can also be thought of as planetary circulation. Hot material rises from near the core, cools as it nears the crust, and sinks again to be reheated. The cycle repeats endlessly, driving the drift of continents, the birth of oceans, and the renewal of crust. Without it, the planet's heat would remain trapped, and tectonic activity, the source of mountains and volcanoes, would cease. The Earth would grow rigid and lifeless, its surface frozen in time. Instead, it lives through movement, balancing heat and gravity with quiet precision. This slow rhythm produces the patterns we see on the surface: chains of islands, mountain arcs, and deep-sea trenches. Each reflects the hidden geometry of convection below. The crust shifts because the mantle flows. Volcanoes rise because pressure seeks release. It is an elegant system, one that self-regulates, keeping the planet neither too hot nor too cold. The same physics that stirs magma beneath your feet also shapes the moonless plains of Mars and the stormy clouds of Venus. Across the cosmos, motion prevents decay. The energy that drives this process comes from two main sources: residual heat from Earth's formation and the slow decay of radioactive elements in the mantle. The decay of uranium, thorium, and potassium provides a steady release of energy, tiny particles colliding and transforming into warmth. Though imperceptible moment to moment, their collective effect sustains the Earth's interior temperature over billions of years. It is a perfect balance between exhaustion and renewal, between heat lost and heat produced. The result is a planet that cools, but never fully, rests, but never sleeps. Every earthquake, every eruption, every new volcano is a small exhalation of this internal energy. To scientists, these events are data, measurements of stress and temperature. To nature, they are simply maintenance, the same way a body adjusts its breath or a tide corrects its pull. The planet releases energy to stay in balance. Its occasional violence is only the visible edge of a deeper harmony. If we could listen closely enough, we might hear that rhythm in the background of everything, a low, continuous vibration under the oceans and continents. Seismic instruments recorded as microsisms, faint tremors produced by waves colliding across the globe. The earth hums, softly and constantly, a note too low for human ears. Some researchers call it the seismic whisper. It is the sound of energy finding its way through rock and back again, the sound of equilibrium sustained through motion. There is comfort in that idea. It means the ground you rest on is not inert but alive in a steady, dependable way. Beneath its apparent stillness, it carries the same patience you seek when you slow your own breath. You are supported not by silence, but by movement too slow to disturb. The planet's pulse and your heartbeat exist together in this same moment, separated by scale but joined in rhythm. As you prepare for rest, let that image guide your breathing. Inhale as heat rises, exhale as it falls back into calm. The motion is infinite and effortless, a mirror of the Earth's own flow. You do not need to search for sleep. It arrives naturally when the inner pulse and the world's pulse align. Think of the mantle currents far below you, steady and sure, shifting continents with a patience that spans eternity. You, too, are part of that same continuity, warm at the center, calm at the surface, balanced by slow movement and quiet release. Tonight, let the hum of the planet carry you. Its rhythm is older than life, older than oceans, older than the air itself, yet it continues, gentle and unbroken. The ground beneath you is never truly still. It holds you in motion so subtle it feels like rest. Sleep then, within that movement, peaceful, supported, and perfectly aligned with the living earth. Humanity's relationship with volcanoes began with awe and fear, but it evolved into understanding. Today, scientists measure what ancient observers could only imagine: the heat, the gases, the tremors that precede an eruption. The modern study of volcanism transforms mystery into knowledge, allowing us to anticipate danger and learn how the planet's deepest systems behave. To study a volcano is to watch the Earth think in slow motion. The science of volcanology combines multiple disciplines: geology, chemistry, physics, and atmospheric science. Instruments placed on the flanks of active mountains record vibrations so subtle that only machines can detect them. These seismic signals often form a pattern known as harmonic tremor, a rhythmic vibration that indicates magma moving through narrow conduits. Global networks of sensors capture such data in real time, creating an early warning system capable of saving lives. By listening to the Earth's smallest quakes, scientists can predict its loudest moments. Another vital measurement is deformation, the slight swelling of a volcano's surface as magma accumulates below. Using satellite radar and GPS, researchers can detect changes of just a few millimeters. When combined with gas measurements, especially the release of sulfur dioxide and carbon dioxide, these signals reveal a volcano's breathing cycle. An increase in gas without corresponding uplift might suggest new pathways opening. Rapid inflation could mean magma is nearing the surface. Each dataset contributes a piece to a complex puzzle that helps forecast eruptions. The chemistry of volcanic gases tells its own story. Instruments called spectrometers analyze light passing through plumes, identifying the composition of gases and their ratios. A rising proportion of sulfur dioxide, for example, often precedes explosive activity. These gases also carry clues about magma temperature and depth, giving scientists insight into conditions far below. What once appeared as mysterious smoke is now a coded message that technology can translate. Volcanic monitoring does not end with observation. It requires interpretation. No two volcanoes behave alike, and each has its own character. Some, like Kilauea, release frequent, predictable flows. Others, such as Mount Pinatubo, remain quiet for centuries before a single, massive eruption. Teams of scientists model these differences using computer simulations that replicate magma movement, gas expansion, and crustal stress. The results guide evacuation plans and hazard maps, helping communities coexist with geological uncertainty. Remote sensing from space has transformed this field. Satellites equipped with thermal cameras can detect heat anomalies on the scale of meters, revealing new vents and lava flows even in remote regions. Volcanic ash plumes, which can disrupt aviation and climate, are tracked across oceans in real time. What once took months of observation can now be known within minutes. The Earth's activity has become part of a continuous global dialogue, its signals captured by instruments orbiting hundreds of kilometers above. Yet for all its precision, volcanology remains a science of humility. The best instruments can predict probabilities, not certainties. A mountain can sleep longer than data suggests, or erupt sooner than expected. The planet maintains an element of unpredictability that resists full control. Scientists learn to read signs without presuming mastery, to translate motion into meaning while accepting that nature speaks in approximations. That humility is part of the discipline's strength. It fosters respect as well as knowledge. For the rest of us, these measurements reveal something deeper than risk management. They show that the planet is not chaotic but comprehensible, governed by laws we can observe and patterns we can follow. When we measure a volcano's pulse, we are really measuring the continuity of the Earth itself. Each reading, each signal, each plume recorded is a reminder that the world remains active, alive, and generous with its secrets. As you drift toward rest, imagine those instruments quietly recording through the night. Sensors humming, satellites watching, scientists interpreting the Earth's whispers. Their work continues while you sleep, part of a collaboration between human curiosity and planetary motion. The volcano breathes, the data flows, and knowledge deepens without haste. The world keeps its rhythm, and so can you, steady, patient, quietly aware of the balance between power and peace. Volcanoes are not only part of the planet's history, they are woven into our own. Across cultures and centuries, humanity has watched these mountains burn and tried to understand what they meant. Long before the language of science, people sensed that volcanoes were more than destruction. They were expressions of the same energy that animates life itself. Fire rising from the ground became a symbol of renewal, purification, and creation. Ancient civilizations built myths around these fiery peaks. The Greeks imagined Hephaestus, god of fire and craft, forging weapons for the gods beneath Mount Etna. The Polynesians honored Pele, whose temper shaped the islands of Hawaii. In Japan, Mount Fuji became a sacred symbol of endurance and beauty, embodying the unity of earth, air, and fire. Though the names differ, the message remains constant. The same force that destroys can also create. Each eruption was both a warning and a promise, a demonstration that life emerges stronger after the storm. Modern psychology might describe this relationship as projection, the way humans recognize parts of themselves in nature. The volcano mirrors our inner landscape, pressure building, emotion rising, release followed by calm. Like magma beneath the crust, the energy within us can be creative or destructive depending on how it finds expression. Controlled, it becomes art, invention, or passion. Suppressed, it can erupt in anger or despair. The lesson of volcanoes, therefore, is not to fear intensity but to channel it, to let what burns inside be shaped into something constructive. Even in art and language, volcanic imagery persists. We speak of explosive tempers, boiling frustration, and fiery ambition. Poets describe hearts that erupt with love or smolder with grief. Scientists might separate metaphor from fact, but emotionally, the parallels remain valid. Both magma and emotion follow the same principle. Pressure must find release. When it does, the system stabilizes. When it doesn't, cracks form. The mind, like the planet, thrives through movement and renewal. On a physiological level, this analogy reaches deeper. The minerals that flow from volcanoes, iron, calcium, magnesium, are the same elements circulating in our blood and bones. What the earth releases becomes part of living bodies. We are literally composed of recycled stardust and cooled lava. Every heartbeat carries traces of ancient eruptions. Every cell echoes the chemistry of molten rock transformed into life. In this way, volcanoes are not distant phenomena, but ancestral origins. Their fire lives quietly within us, not as destruction but as warmth, metabolism, and thought. Cultures that live near active volcanoes often express this kinship through ritual rather than fear. In Indonesia, offerings are placed at craters to honor the spirits of the mountains. In Iceland, geothermal springs provide warmth and energy, turning volcanic heat into comfort. The same landscape that threatens is also cherished, reminding people that harmony comes not from control but coexistence. Humanity's long survival beside volcanoes proves our capacity to adapt, to find safety in unpredictability and meaning in raw power. Science now explains what myth once described: energy cycles, mineral transformation, tectonic balance. Yet knowledge does not erase wonder, it refines it. Understanding how a volcano works deepens our sense of connection rather than diminishing it. To know the chemistry of fire is still to feel its beauty. The rational and the emotional, the measurable and the spiritual, all converge at the edge of an active crater. As night gathers, think of that shared fire, the energy that moves planets, drives storms, fuels stars, and keeps your own body warm. It is the same current flowing through every scale of existence. You do not need to separate yourself from it. You are part of it. When the world feels heavy or restless, remember that rest is not the absence of motion but its softer form. The fire within you, like that within the earth, does not vanish, it simply changes expression. Tonight, let it settle into calm glow, steady and enduring. If one could watch the earth from its beginning to this moment, the story would read as a cycle of endless renewal. Every continent, every mountain, every island has been made and remade by fire. Volcanoes, in their silent intervals and sudden awakenings, serve as reminders that the planet itself never stands still. What seems fixed is only momentarily at rest. Even the oldest rocks, stable for billions of years, were once liquid, reshaped by heat and pressure before finding calm. Scientists can trace this renewal across deep time. Layers of volcanic ash buried in sediment record the rhythm of eruptions that have shaped climate and evolution. Some eruptions cooled the world, dimming sunlight for years. Others released gases that warmed the atmosphere and accelerated life's diversification. The planet's balance has always depended on this delicate conversation between eruption and erosion, destruction and recovery. The surface is not a static shell, it is a skin that heals itself continuously, through fire and weather, uplift and decay. Every volcanic event contributes to the Earth's memory. When a mountain explodes, its fragments become sediment that drifts into oceans. There, minerals settle, harden, and eventually rise again through tectonic motion to form new land. The same matter that once flew as ash may return as mountain. This recycling defines the very essence of a living planet. Unlike the Moon, where craters remain untouched for eons, Earth renews itself through perpetual transformation. It erases its scars not by forgetting but by turning them into new landscapes. This principle extends beyond geology. In biology, renewal mirrors the same pattern. Forests recover after fire. Coral reefs rebuild after destruction. In the human body, cells replace themselves constantly, maintaining form through change. The rule is universal. Endurance arises from renewal, and renewal from release. What volcanoes enact on the scale of continents, life repeats in every heartbeat. The flow of energy through matter, the passage of heat, motion, and time is the foundation of everything that persists. When scientists model the long future of Earth, they see this renewal continuing until the planet's heat eventually dissipates. Billions of years from now, volcanism will fade as the mantle cools and the tectonic engine slows. Continents will drift into new configurations. Oceans will change shape, mountains will rise and vanish. Yet even as activity declines, the principle remains: creation through transformation. The last volcano will not mark an ending but a final exhalation in a story of continuous change. What began in fire will end in calm, but the legacy of that motion will endure in stone and memory. For us, that truth offers both humility and comfort. The same processes that shape planets also shape lives. Renewal demands acceptance of impermanence. What ends does not vanish, it becomes something else. Every difficulty, every collapse, every release contains within it the potential for rebuilding. The Earth teaches this lesson not through words but through motion, slow yet unstoppable. Stand on any volcanic plain and look around. You will see grasses growing in ash, rivers cutting through hardened lava, and clouds drifting over mountains built by ancient eruptions. Everything visible is the outcome of earlier destruction, yet it feels peaceful. The quiet is not emptiness, but resolution. This is what recovery looks like when measured in geological time. The world breathing in again after a long exhale. As you prepare to rest, let that rhythm settle in you. Think of the planet as an immense heart beating through its eruptions and silences alike. The same pulse that drives continents drives your own renewal. Each day, you shed and rebuild, adapt and continue. Just as the Earth finds balance through change, you find peace through acceptance. There is no need to hold on to what was. Everything moves forward naturally. The fire cools, the land steadies, and new forms emerge. The cycle endures, calm, patient, eternal. The story of volcanoes is, in the end, the story of Earth itself. Beneath every ocean and continent, the same quiet forces continue their work, melting, shifting, rising, and cooling. To know volcanoes is to see the planet as a living organism. It breathes heat instead of air, moves in centuries instead of seconds, and finds balance through transformation rather than rest. The fire that began this world still glows beneath your feet, and its warmth has never faded. Every eruption, no matter how distant or ancient, has contributed to the world you inhabit. The mountains that cradle rivers, the minerals in soil, the gases in the atmosphere, all trace their origins to volcanic release. Even the oceans exist because water vapor once escaped from molten rock and condensed in the sky. The shape of continents, the fertility of valleys, and the thin blue air above are not coincidences. They are gifts of geological breath. You walk each day on cooled fire, carried by the memory of creation. In that sense, the Earth's surface is a dialogue between destruction and renewal. Where lava once scorched, forests now grow. Where ash once darkened the sky, fertile fields now feed generations. Each transformation leaves traces, minerals rearranged, ecosystems reborn, and climates adjusted. Scientists map these transitions like historians reading layers of time. Each stratum of rock is a page, and together they tell a story not of chaos but of resilience. The planet has endured ice ages, collisions, and mass extinctions, yet it continues, adapting with a patience unmatched by any living being. We often imagine the ground as solid and unchanging, but in truth, it flows in slow motion. The continents drift across a mantle that moves like an unseen tide. Volcanoes rise, erode, and return to the deep. Even the tallest mountains are temporary sculptures carved by gravity and time. The steadiness we feel underfoot is not the absence of change. It is the perfect balance of forces too vast for us to perceive. Stillness, on a planetary scale, is motion stretched across eternity. When viewed in this light, the boundary between the human and the cosmic grows thin. Our lives follow similar patterns: pressure building, transformation unfolding, calm returning. What feels like upheaval is often a step in renewal. Just as magma must rise before it cools into land, moments of intensity in our own lives precede growth. We are not separate from the Earth's rhythm, we echo it in every heartbeat and breath. If you could listen closely enough now, you might sense it, the faint, continuous hum beneath the noise of life. It is the low vibration of tectonic motion, the whisper of heat moving upward through stone. It is also the rhythm of your own pulse, steady and present. The two are aligned, the planet's deep breath and your own. Both remind you that energy never disappears, it only changes form. The warmth of magma becomes the soil that nourishes life, and the warmth of your thoughts becomes the calm that carries you into rest. Let that awareness settle around you now. The world outside is dark and quiet, but beneath that quiet lies motion and care. The ground supports you not as something static, but as something alive, holding you gently in its long rhythm. The planet cools slowly, just as your body cools towards sleep. The same forces that built mountains are now at peace beneath you, still warm, still kind, still endlessly patient. If sleep comes to you now, let it be like the cooling of lava, heat turning to calm, energy to stillness. You do not fall away from the world when you rest. You fall deeper into its pattern. You belong to a living earth, shaped by fire and renewed by time. In this moment of quiet, the planet's ancient pulse moves through you, steady as breath, soft as the night itself. We, from Sleepy Stories, wish you a good night.